Yes, it is started. You can continue.
Yes, sir. Thank you. So, Dr. Venkateshwar did his degree in metallurgical engineering and MTech in engineering materials from NIT Bhopal in 1995, and he completed his PhD in metallurgical and materials engineering from IIT Kharagpur in 2000. He is presently working as senior principal scientist at CSIR NAL Bangalore, and is working in CSIR from past 36 years. He is the recipient of Professor B. Banerjee Memorial Award for his best MTech thesis in 1996. And after that, he had been to Japan for 6 months to undergo advanced training on NDT. In 2004, he went to University of Southern California, Los Angeles, USA for his postdoctoral work. In 2009, he went to Russia and presented his work on ultra-fine grained aluminum alloys. In 2011, he went to China and presented his talk on nanostructural aluminum alloys. During September-October 2014, he visited Miskolc University, Hungary, and delivered talks on advances in processes on of aluminum alloys. On his personal trips, he visited Germany, Belgium, Switzerland, France, Slovakia, Bhutan, UAE, and Hong Kong. In 2015, he went to Shanghai and chaired a session in an international conference and also presented an invited talk. Dr. Venkateshwarlu has published 103 international papers and 145 national and international conference papers. He has guided 7 MTech and 20 PhD students. Recently, he got a R&D project for rupees 1.8 crores as PL from defense sector. He is a fellow of Institute of Engineers, Kolkata, CSIR Raman Fellow, Professor of Academy CSIR, and Fellow of Andhra Pradesh Academy of Sciences. So, with a small introduction, now I hand over the session to Dr. Venkateshwar. Sir, over to you.
Good morning, Dr. Raju and Dr. Tejas. I don't know whether you can able to see my PPT.
Yes, sir, we can see your screen. So, if,
Sir, you can share your entire screen, sir. Then it will be visible fully, sir.
Now, can you able
Yes,
to
sir.
see?
Yes, sir. Yes, sir. Fine, sir. Absolutely fine, sir.
Thank you for the nice introduction, Dr. Raju and Dr. Tejas. And today I will be talking for another 1.5 hours. Whether you people are interested or not, you are going to listen for another 1.5 hours. There is no option left for you. Only thing you can keep your screens off and you can do your own work. But I am going to talk on fabrication of nanostructured aluminum alloys using severe plastic deformation method. I think I'm going to cover what is grain refinement, what is severe plastic deformation, why do you require such a fine grain structure. All these points I will be discussing. This is the work over the period of 3 decades, what we are doing for different institutes. I'll be presenting this talk. Basically, my name is K. Venkateshwarlu and I am from CSR NAL Bangalore. I think most of the people, when you keep your name as K. Venkateshwarlu, I think this is not the correct forum to say that you should not write the K. Venkateshwarlu, it should be written Venkateshwarlu K. I think Dr. Raju is always writes Venkateshwarlu Karodi. That's what he is always correct in his way of putting the name. Why? Because Venkateshwarlu is the first name and the surname is K, stands for Karodi. So this is the way it should be. I think it has a lot of meaning when you have your name. So don't play with the name at all. Since I am writing for all scientific papers as K. Venkateshwarlu, here also I put K. Venkateshwarlu. But some of South Indian people, they write name as surname first. That is not correct. It should be written as Venkateshwarlu Karodi only. With this small introduction, I think he has given a brief introduction about me. I think I will also briefly say that. Before that, let me sincerely acknowledge my thanks to Dr. T. N. Raju, who is the backbone of this FDP program for 5 days. That is on recent advances in composites and nanomaterials. I think he asked me to give on nanomaterials. Even though I have done a lot of work on composite materials, which I am not going to cover in this portion. Why? Because metal matrix composites, we have extensively worked on aluminum based metal matrix composites. I think, but he suggested me that I should talk something on nanomaterials. which is the FDP program for 13th and 17th December 21. I think people must be knowing that the difference between an international conference and FDP programs and seminars and symposiums. You should have that basic idea why you should be. This is particularly development of the faculty program, where senior people or experts from different institutes will give their experiences, where you can take some of the things. I don't think that whatever I am presenting, it will be 100% useful. At least if you can able to take 1 or 2% from this lecture, I will be the happiest person for that. I think after sincerely acknowledging the services and hard work rendered by Dr. Raju and his team from Dr. AICTE, I would like to thank my PhD students, Akimadi, Dr. Sidhu, they are from BEC Bagalkot, Dr. Manohar, Dr. Patil from KLE Belgaum, Dr. Prasad from BIT Bangalore, and Dr. Prabhakar from KLE Hubli, Dr. Jaya Christian from MSRIT, Dr. Bharat from Global Academy of Technology. These are my people where I have signed as a PhD supervisor. However, there are some other people who I have not signed, particularly Dr. Prasad from HAL, Muzamil, Nagakrishna, Vigneshwaran, Mustaf, and Gopal Krishna, Rajendra. I think he is from Dr. AIT, IE department, Dr. Gopi, Mohan, and Prabhudev. I think he is attending this talk. I think we have good interaction always. He keeps taking the advantages of taking the guidance in particular. And Dr. Krishna and Dr. Reddappa, these are the people with whom I have directly supported for their PhD degree. I think if you can see my resume briefly, I have done around 12 years in central part of the country, and afterwards I have moved to National Metallurgical Laboratory, Jamshedpur, east part of the country for another 12 years. Then I shifted to NL Bangalore, South India, for another 13 years. This all including my services for 37 years. That includes 3 years as adjunct faculty. I was a professor at NIT Jamshedpur, teaching for mechanical and metallurgical students, final year students, and I am also a professor for ACSIR since 2017. With this small brief introduction about me and what I am going to talk, let me give a brief content of what is I am going to talk for another 1 hour 25 minutes. That is what is material science, where we are standing, and particularly when you are talking about grain refinement of aluminum alloys, and what are the various methods for grain refinement of aluminum alloys, and how severe plastic deformation is useful for grain refinement. That is, when you are doing grain refinement with the different methods, why we should select severe plastic deformation. And today's lecture is on nanostructured materials. This I will be talking on at the end of my talk, that is high pressure torsion, where we have done one of my student, Dr. Patil, has done extensive research work on this one, on 7075 and 2024 alloys, where he could able to show that these materials can develop nanostructures, and it can lead to something like 1100 MPa, YS and UTS. And before that, I will talk about repetitive corrugation and straightening, where we can develop ultra-fine grain structure. Extensive research work was done by Dr. From KLE Belgaum, Prabhakar, and some of the tips what you can take from this talk, this I am going to explain you. Let me come to the material science, what is happening in traditional theme mainstreaming material science for the past 5,000 plus years. Why people are more interested in material science principles. And if you see clearly, the first part is basic material science principles. This everybody should understand what are the principles. That's what I emphasize all the faculty members and the students, that if your principles are very clear, I think you can go on giving answers for anything. The concept should be clear. So for this, you should understand the basic nature of the materials, what are the principles are required. Then the next part is try to understand the materials, and once it is processed, what is the microstructure it is coming. There is a big difference between a mechanical engineering and material scientist. That is, when a material which is required a high strength, if you get the high strength and high ductility, the mechanical engineer, he will feel very happy. But a material scientist or metallurgist wanted to see the microstructure, how it is refined, why the strength has been increased. These are the points a material scientist will look into. And after that, the third point is part three is properties and applications. Once the microstructure is differed or changed, what properties you are going to get, why it should be given only strength and ductility only, why not other hardness and other properties. And finally, we have to see the application. This is the most important part of my talk. I think I am going to talk to you, all the people, about application part is very important. Why? Because when we are doing a research at AMPRI Bhopal, that is a regional research laboratory Bhopal, what we have done is we have developed a lot of composite materials, aluminum based composite materials are like aluminum SiC, aluminum TaO2, aluminum graphite, aluminum, what all type of. Why? Because that time there was some scientists who joined from IIT Kanpur as a scientist junior level, and everybody started doing the PhD work. And if you all know that, we should not forget the contributions made by Professor Pradeep Kumar Rohatgi, who is now in Wisconsin University. What he has done is he is a man of composite materials. I think you can see ASM handbook also, somebody reads that book, you can see the chapter on composite materials by Professor Rohatgi only. So there we have done a lot of research work on aluminum composites. Later on, after I shifted in 1999-97, people started application part. That's what I am interested in, application part, where they have gone for the application part. Bajaj Auto and other things, they have changed all the rare hubs and everything they have changed with using the aluminum SiC composite materials. And even for armor applications also, CFRP, they wanted to remove and try to see that how this aluminum SiC composites will work. That is the part of composite materials. Later I shifted to Jamshedpur, where I was doing a lot of work on aluminum grain refinement, and if you process those things, how it will, microstructure will change, how properties will change. But when we came to NAL Bangalore, there we have seen that application part is more important. It is not the question of fundamental research. Anyway, you have to do the fundamental research work, but you should not forget that finally what is going to lead in this your research work. I think nowadays I am sitting in a lot of conferences and project sanctioning authority, as a sanctioning authority, where we can see that the students or the faculty members, they try to explain what work they are going to do in their work. But finally, if you ask what is the component you are going to make, or where you want to replace, or what is the output of this one, they are a little lagging in this one. And finally, what they say is, sir, we have not attempted this one. We wanted to study in the laboratory level. Those are all accepted, but you must say that finally what we are going to, application is more important. So let us see that nanomaterials, why that nanometers, how the scale will be changing. If you see a ant which is around 5 mm length, and if you see the fly ash particles around 10 to 20 microns, I think human air will be 60 to 120 microns wide. This is the distance. Now another one more interesting thing is, whenever somebody present any work, I think from easily we can find out what is the width of this hair, or what is the length by seeing the micron bar. You can see here there is a micron bar in ant structure. You can see that. From that we can easily find out that what is, suppose if you say that this is 60 to 120 microns, instead of that you say that it is 500 microns, we cannot accept that one. So even if you see that fly ash particles here, those are all around 10 to 20 microns average size. And you can see the blood cells. Then you can go on seeing the 10 nanometer diameter, and you can see, go on seeing like this variation of microns to millimeters to micron, micron to nanometer range. This is the nano world and micro world. Nowadays, one more suggestion to all the faculty members would be, since now people talks about nanomaterials, it is not like that you just jump into the nanomaterials and start writing some proposal and do some research work. You require a fundamental aspect why we should do the nanomaterials, and whenever you submit a research proposal on nanomaterials, you should see the application part. That I will take one case where we have miserably failed. I will tell about that case study also at the just before the conclusion of my talk. Now you can see that whatever self-assembled nanopied structures 10 to the power of 5 nanometers are nanotube electrodes. So you can see this one. This is the CNTs. Now people are working on CNTs and graphene. I think the day it is going to come that you will be having a lot of graphene materials and CNT materials. Even your laptop also is going to be changed with a graphene material where you can enlarge or with your hand only. If you want to talk, you can record it and it will nicely present everything. Those things will come. And you can see that the quantum coral of iron atoms in copper surface, you can, what are the atoms are there? Nowadays, the facility has come that in nanostructure, you can remove that atoms and keep another atom also. This type of studies are also is coming in a big way. I think before going into our lecture, let us have a brief idea about what type of advanced materials are there and what type of aerospace materials we are talking, why we should go for aerospace materials only. Why? Because we are working for aerospace material. Whenever you say any advanced material, the definition should be any new or significantly improved material that provides a distinct advantage in performance when compared to the conventional material. Suppose if you are using a conventional material of aluminum copper system, and if you are making any advanced material with aluminum copper system, you should have the strength and property should be enhanced. That is main, that's what it should be called as advanced materials. And what type of materials you can talk about is metals, semiconductors, ceramics, and polymers. And nanomaterials and biomaterials and energy materials. These are the materials where we can talk of, consider as advanced materials. Coming to aerospace materials, where we are doing a lot of research work, is aluminum lightweight structure materials. Why? Because it is inexpensive and state-of-the-art is available. And new composites and alloys like titanium, graphite, and fiberglass. People, those who are working on these things, titanium, graphite, and fiberglass, they should invent this, try to work on these materials. And carbon nanotubes, as I told that now carbon nanotubes and graphene material, it is going to be shifted along. As I said, in aerospace sector also, earlier we are using a lot of aluminum alloys. Now this fiber reinforced composite material and glass fiber reinforced composite materials, they have shifted almost, they are taking 50% of the total components for an aircraft system, and polymer composites. And we should understand the delamination. What is delamination? Why? Because there is a big issue when you are talking about the composite fiber composite materials. Why? Because these fibers are aligned in one direction, whether it is a UD, BD, or MD, that is multi-directional, and delamination is going to take place. And glass fiber reinforced composites and polymer matrix composites. Why some of these composite materials still the metallic structures and metallic composites still existing, they are unable to replace the polymer composite materials are unable to replace the metallic structures, is the main issue is a catastrophic failure. Whatever you are talking about, FRP or GFRP or PMC composites, where you can see that the catastrophic failure. That means whenever there is suddenly failure takes place, and it may lead to accident. Whereas in case of metallic materials, it doesn't happen. The crack has to initiate, it has to propagate, then finally it has to be failed. So this is a lengthy process which may take more than 4 months, 6 months or so. So in order to avoid that catastrophic failure, the metallic materials or metallic composite materials are still existence, and people are working in polymer composites also, how we can avoid this thing. These are the points where somebody is really wanted to do some research work. They should concentrate on these aspects. Let us talk about aluminum alloys. What is the importance of the grain refinement for a few minutes, around 6 to 8 slides on grain refinement. Then we will try to see that what are the methods available for grain refinement. Then we will go for the severe plastic deformation. It is in general defined as the deliberate suppression of, you can see here, the columnar structure is deliberately suppressed to fine equiaxial grain structure, and you are going to achieve. Why? Because Hall and Petch, these are the two scientists who has told that sigma y is equal to sigma 0 plus k d to the power of minus half. D to the power of minus half is nothing but the diameter of a grain size, where you can reduce the grain size, the yield strength increases. That's what they have did. In 89, McCartney, he has those who are doing particularly research work on some of the materials called aluminum alloys. If you are talking about somebody has put a significant research contribution for grain refinement, what happens is every 10 years there is a metal review in material science, that is Metals International Review. One paper is there which is having something like 250 to 300 references should be there, and which is having almost like a one thesis. It will come, this total paper. So 89 McCartney has written, 99 our group, Professor Corey, Professor Murthy, and Professor M. Chakravarti, they have written one International Metals Review IMR paper, which is considered as a Bible of most of the people, those who are working on grain refinement. They consider this paper is one of the best paper. And what we have seen is not only we are giving that contributions made by other people, and also what are the contributions made by our group also. This is most important when you write a IMR paper. And if you see that in particularly grain refinement, how these small scale industries, how they are experiencing this practice, grain refinement practice, whether they add as aluminum titanium master alloys or aluminum titanium boron master alloys, what they can do is, in industry you can see that there is a plunger where that aluminum grain refiners are put in the plunger, and just what they do is they insert into the liquid metal where the gases comes. Why? Because these are the fluoride gases which influences your health conditions also. So this is the old practice. People still started using this master alloy addition levels, and you can see that one once the master alloy is added like this, they can take it out, and that is all ash products of whatever this thing. But suppose if you are having a practice in large scale industries, that's what a basic understanding is. When you are doing a grain refinement, what is the influence of that holding time? You see here, you are keeping a large number of ladles, and you are having a crane which is holding a ladle of liquid aluminum. And when you are pouring this aluminum and grain refiner into this one, and you are going to continuously pour this one, it starts from a minute to a 30 minutes maximum, half an hour it will take to pour in all the dyes. But in this practice, the holding time, why? Because when you are adding these grain refiners, you should be able to understand that you can see that now liquid aluminum has come, and this is where the industrial practice, where you need to, the master layers are fed into the liquid aluminum, and he is pouring into different molds. And you can see that when he is pouring here, the master alloy is in a rod form, or it is in extruded form. It is added to the same mold. He is already pouring that one. Once he has completed this pouring in one mold, he will go to next mold, and again he will pour to another mold. So here you should understand that say now he is going to another mold with the crane facilities. So it takes almost like 30 minutes, but we have done studies up to 60 minutes of time. What happens after grain refinery is added? So what are the other methods are available for grain refinement is inert gas condensation and mechanical alloying. Now people are working on mechanical alloying. They take elemental powder forms of different metals, and they combine into mechanical alloying process and make some of the unconventional materials also. And another method is rapid solidification, and the method which is available for a bulk materials is a severe plastic deformation, where I have done my postdoc at USA on severe plastic deformation of alloys with Professor T.J. Langton, who is known as one of the world-renowned scientists. Nowadays, all the scientists are researchers who are in a particular field. They have their ranking numbers. So he is world number 3 in material science. I think there is a website called insights.com where you can go and put your name and check that where you are standing in your research work. That I think I would have talked for another 1 hour on this issue. But prior to that one, let me talk about grain refinement of aluminum alloys. What are the mechanisms here? We are adding the grain refiners like aluminum titanium boron, and aluminum titanium carbon. And there are 3 methods are available. Basic theory is phase diagram theory, that is a liquid reacts with titanium aluminates, and alpha aluminum is forming around 665 degrees centigrade. And there is a carbide theory which says that whether intentionally, whether you add a carbon or not, it will pick up some carbon with the titanium, and it makes titanium carbide, which is thermodynamically it is not stable. However, people shown that these TIC particles acts as a grain refiner and nucleating sites, and there is a grain refinement effect. And there is another theory called boride theory, which is known as TAP2 and aluminum, titanium, and boron boride theory. This is what Manohar and Prabhudeva, they have done a lot of work on this one, along with Sidhu from Bagalkot, Basveswara Engineering College, Bagalkot. And what they have shown is whenever this heterogeneous nucleation starts, you can see that the particles, when a liquid, how it comes. This is the heterogeneous nucleation principle, and why they are acting as effective nucleating sites. Why? Because what are the conditions, what are the required for this nucleating sites? The melting point of Li being solidified, it should be greater than the nucleating site, able to initiate freezing at very small undercooling effects, sufficient number of nucleating particles should be uniformly distributed, and nucleating particles should be larger than critical size, which depends on the undercooling. I think if you want to understand this one, if you see the lotus leaf, where you can see the particles, water particles doesn't stay. Why? Because it is super hydrophobic in nature. Why? Because this contact angle is more than 150 degrees. So it will not stay in that one. So we are also working on super hydrophobic coating. And now coming to the aluminum industries, basically if you see that there are primary industries, Balco, Nalco, Hindalco, Malco, and secondary industries like small scale industries are available. And when we have developed some new material, I think we did a significant of work on developing some aluminum, magnesium, scandium, zirconium alloy, and we wanted to go for this alloy within a sheet form, where we have contacted all these people where they said that we cannot stop our production for your new alloys. Why? Because per day the huge crores of rupees they are going to lose. And small scale industries, they are depending every day, they get a benefit of some profit of 10,000 to 20,000 rupees. They say that if I do your research work here, it is very difficult for us to maintain our profit business. So they are also not interested to go for this small scale industries also. So we have to finally get our materials 2.5 meter by 4 meter sheets with our own composition. We could able to get it, and now plenty of materials are available. And we have developed this aluminum, magnesium, scandium sheets, and now when primary industries, secondary industries, they are not giving importance to our research work, then where to go? That is a big question. And who will support, how to convey this one, what we can do. These are all the problems, and we could able to come all the problems. Why? Because financially we are good in the aerospace sector, so we could able to around 25 lakhs we have spent, and we got the materials for another decade. We can work on this one. So as I said, in the holding time in industries is more important. What is the, we are not doing something which is why we are doing for 60 minutes and 120 minutes holding time. Why? Because the crane which carries that liquid aluminum and pours into the ladles, it will take some time. So that's what the holding time is more important. And what type of master alloys or grain definers modifiers should be added to the liquid aluminum, and what is the influence of rolling and extrusion of these master alloys. So here you can see that that is the whole normal grain size versus holding time. So once you say that optimum contact, generally it is referred as 220 microns. I think people should be understanding that why we are considering. There is a one paper in which they have clearly shown that above 220 microns, it is not grain defined. So one level they have achieved, and by adding this one, we have seen that there are three different types of grain definers. One is you can see that grain says as holding time. That's what holding time is very important. You can see that the holding time is slow acting in number one case, and number two case it is fast acting but early fading is taking place. But in third case, if you see that it is fast acting but it is long lasting, this is ideal for any grain definer to be made. So we have made a lot of grain definers. You can see that how the grain refinement, that's what this is in minutes. You say that without any commercial, these are all commercial aluminum we have taken, and without any addition of grain definer at 0 minutes. And after adding the grain definer 2 minutes, 5 minutes, 30 minutes, 60 minutes, 120, even those 30 minutes would be sufficient, but we have done extra work and seeing that any fading effect takes place or not. And these are the grain definers which we are talking about. I think I will not give much details on grain definers. Why? Because we will talk on severe plastic deformation. This is the common grain definers like titanium boron mixture, and these are all used as a flux. Why? Because people initially they found that this titanium and boron can be added as an elemental form, but K2TF6 and KBF4, these are the salts which are available. So they made a master alloy from this one. So 1 hour holding time in induction furnace, it made as a master alloys of aluminum, 5 titanium, 1 boron, aluminum, 3 titanium, 1 boron. I think we have made a lot of aluminum grain definers. I think extensive research work was done. And most of these grain definers are hygroscopic, can cause to increase porosity, advisable to degas after nucleation. This is the some of the comments which and let us see that what is happening in conventional material processing. Why? Because we already started, we'll talk about severe plastic deformation. Before that, let me have some 2-3 slides suggesting that what we should do on conventional, what is happening in conventional material processing. If you see that any rolling process, when the particular rolls, if you are having a height of this much and it is reducing to h, this is the rolling direction. And what is happening into that rolling when you are doing what type of microstructural changes. If you see the columnar grain structure here it is a completely a columnar grain structure when you are starting before rolling. After rolling, you can see that it is proceeded to static recrystallization, and finally what happened, we can see that the static recurrent grain growth has happened, and we can see a fine equiaxial grain structure. This is what is intended to have this by rolling process. Similarly, people are doing with forging. Why? Because now you are not expected any defects in the material, so that what you can do is you can use the forging technique, so that what are the workpiece you are having, you have a lower die and upper die, and just apply the pressures, so that what are the dendritic structure you are having, that will become a equiaxial structure or non-dendritic microstructure it forms. And this is the where 500 ton press and 1000 ton press, such presses are used as a forging material. But nowadays rapid prototyping is coming in a big way. I think those who are working on rapid prototyping, they have facility of creating such a microstructure as received condition itself. You can print to this microstructural details. So people, those who are working on rapid prototyping, it's a very good work, and the contribution he has made, Dr. Jaya Christian from MSRIT, he has done extensive work on PLA material and ABS material, where he has shown he can print everything and what are the microstructural changes is expected, what mechanical properties are changing, everything he has done in his PhD work. And for your information, even though I am working for more than 3.5 decades, the citation which I was getting for sliding and abrasion wear behavior of aluminum composites, now I got more citations for my what is the work done by Jaya Christian. That is what is important. And extrusion also, you can see that the billet is here. A ram is forcing this billet to form into the extruded product. This is what I have done my research work for IIT Kharagpur, where we have shown that extruded and rolled product of master alloys, how they influence the grain refinement. Extensive research work was done, and we have shown that very clearly that these materials are exceptionally very good. And why? Because why do you require extruded product? Why? Because you cannot add this billet directly to the ladle. If you have seen that industrial practice, the master alloy additions, they made it into extruded products as rods or wires, and they spool it and add into the ladle continuously. This is what is important of the extrusion process. And there are other metal forming methods where you can see the bending and drawing techniques and shearing process. I think those who are having, we are also doing a lot of work on shearing. When we wanted to measure the properties of shear strength, we wanted to, we make some of our own designs and make the shear strength property. This is the shearing, how it is taking place by using the metal forming methods. And recently in 2015, I think there was an international conference on advanced materials and solidification, ICAMS. So it is at Shanghai University, where I was the session chairman and presented some work on aluminum grain refinement work. Let us see that by using the severe plastic deformation, what are the things it is. Initially, A. Mishra, he has clearly given a pictorial view how it is forming due to this severe plastic deformation. Initially, he has discussed it about the ultra-fine grain structure only. Here you can see that the dislocations are forming like this. I think initially you are having a homogeneous distribution of dislocation like this. Then these dislocations are forming, they are touching each other, and you can see that elongated cell formation is taking place. Once this cell formation is taking place, these dislocations are blocking another dislocations by, so that there is a subgrain formation is taking place. If you see this one, there is one grain only. If you see in this case, it is subgrain formation is taking place. And finally, it is going to have some breakup of elongated subgrains and reorientation of subgrain boundaries and formation of ultra-fine grain structure. You can see this one, there is a formation of ultra-fine grain structure. This is what initially he has, this we have done extensive work on aluminum silicon alloys, aluminum magnesium alloys, aluminum magnesium scandium alloys, aluminum silicon scandium alloys. You can refer most of the aluminum alloys, including 6061 also. We have worked on this one, and we have shown that how this dislocations are. I think I will be presenting those TM images. And to achieve these ultra-fine grain structures, there are two methods. One is top-down method and one is bottom-up approach. What is top-down approach is you can take a material which is having a columnar grain structure, and whatever we have said, rolling, forging or extrusion, you can do all the secondary processing. Otherwise, you can go for the severe plastic deformation and you can get the ultra-fine grain structure. There is another one is called bottom-up approach, in which powder metallurgy route is considered, and where you can take that particles which are having already ultra-fine grain structure, and by doing the chemical vapor deposition or mechanical alloying, we can achieve this ultra-fine grain structure in bottom-up approaches. I think even if you see in your college also, if your director or principal wanted to take some decision, one is on top-down approach is he will take some decision, he will ask the HODs to follow that one, the HODs will ask the faculty to follow those instructions. There is another way is bottom-up approach. That is, he will ask the ideas and how to do the things from junior faculty members. Those will be taken by the senior faculty members, and it will be consulted by the head of the department, and he will report to the director. This is the bottom-up approach. So whatever we are doing for materials, it is in practice we are doing in human being also. So I am going to give one slide which I have presented in Russia, that is on severe plastic deformation of all the methods, whether it is a equal channel angular pressing or repetitive corrugation or high pressure torsion. How these methods are there? Why? Because today we are talking about the nanostructured materials which can only be generated through high pressure torsion. And if you see these methods, equal channel angular pressing, what is the principle is, you are imposing a lot of large amount of strain without introduction of any concomitant changes in cross-sectional area. That means if you see here, the cross-sectional area is same as output also. There is only we are cutting that edges part. So what are the grain structure is here, you are significantly reducing this grain structure, and you can see that in aluminum alloys how the microstructure is changing. This I will explain in detail. And AFM structure also, if I take by using the root BC, there are 4 methods are available in this one, and after 4 pass, how it is happening in aluminum 2 silicon alloy or aluminum 2 scandium alloy. These are the various pictorial view I wanted to show that these are all the work what we have done in our research work only. Then the another one is repetitive corrugation and straightening. Initially what we have done is we have taken a hydraulic press, and significant contributions were done by Dr. Prabhakar from KLU Hubli, and initially we have taken the sample like this, and we have made a die of like this, and when you are pressing this one, it will make such a contour shape. This contour shape we will keep it and use the flattened dies and make the sample as it is, so that you can see the improvement and how the microstructure changes are taking place that we have explained here. Now you can see that the RCS is conventional methods, and if you compare with 75% rolled products and how RCS is, if you see the hardness values versus different materials of commercial pure aluminum and aluminum 0.25 scandium, that means addition of scandium is understood. Effect of RCS also is understood from here. Similarly, we have done the high pressure torsion. This is Dr. Patil from KLE Belgaum, and I think when we are doing this high pressure torsion work, initially when we started, why? Because these are the samples are having a 10 mm diameter with 1 mm thickness. You have to make a sample of like this, and you are having upper wheel and lower anvil. I think I have the facility that was created in Bagalkot. This is the first time I think proudly say that we have created this facility in BEC Bagalkot high pressure torsion. Still now, last 2 months back I had been to that place, and the machine still is working. And those who are interested to generate nanostructured in any type of aluminum alloys or any other metals, you can use the facility. You can contact Dr. Sidhu for this work. And if you see that aluminum 2 silicon after 2 turns, so you can rotate this anvil, that lower anvil, half turn, quarter turn, half turn, 3/4 turn or 1 turn, and 2 turns also. You can see that it has the grain size has reduced to 150 nanometers. Where is this 30 nanometers or 40 nanometers in the starting, and the grain size has drastically reduced to 150 nanometers. This is the only process in which we are going to achieve this nanostructured materials using the high pressure torsion method. And let us talk about the ultrafine grain structures where we can do the equal channel angular pressing. And you can see the optical microscope of aluminum 2 silicon in as cast condition. You can see that the grain size is almost like 32. You have a micron bar here, 100 microns. So if I see this one, this comes around 1/3, that is 30 to 35 microns. And Once you have done this one with 4 pass, I told you 1 pass, 2 pass, 3 pass, 4 pass, ECAP, when we have done, the grain structure is completely changing. And even you can see this one, the average grain size also, how it is reducing. And by using the ball indentation technique, I think when you are doing this type of small research work on, suppose if it is a 10 diameter by 100 length, and it is very difficult to get a large number of samples for evaluating your mechanical properties. So what we have done is we have used the ball indentation technique. That is, you indent. This is, we have already patented this one from NML Jamshedpur, and by using the load and deflection, you give the loading, unloading, loading, unloading, unloading, loading. Like that, if you are go on doing that, we have developed a software in which it can give the true stress and true strain values. And you can see that aluminum 2 silicon with the different passes, 1 pass, 2 pass, 3 pass, 4 pass, how this is changing the strength properties or true stress properties, how it is changing. You can see that 4 pass is extremely giving. This was work published in 2006. And we have also done the ECAP work on, we have taken the commercial pure aluminum, and you can see that ultra fine grain structure, almost it is 0.7 microns. It is, this micron bar is 1 micron, it is showing around 15 You can see that 0.7 to 0.6 microns of average grain size. Similarly, we have done an aluminum 3 magnesium Li also, where we have done with the 4-pass sample, and you can see the dislocation network, how it is forming, and these are all the dislocation network. And we have evaluated the mechanical properties of these aluminum magnesium alloys with a different percentage of magnesium, I think 1%, 2%, 3% magnesium. This is the work was done by Dr. Akimadi of Basveswara Engineering College. I think we published in 2018 this work. And what we can see that it is not the question of influence of magnesium content, as the magnesium content is increased. And why people are stopping at 3 magnesium or 5 magnesium is around 4.5 magnesium is, after addition of more magnesium, there won't be much effect. That's what people have stopped at aluminum 5 magnesium alloys only. Now, if you see this, whether 2-pass, you can see that how it is changing, or 4-pass, you can see that how the grain size is changing. Here it is 500 nanometer, this is 1 micron, so this comes around 0.6 microns. Similarly, we have done an aluminum 2 scandium alloy after 4-pass, and aluminum 3 magnesium alloy after 4 passes, and these are all detailed work what we have done and published in Material Science and Engineering A. Similarly, aluminum 2 silicon with 4 passes, we have reviews on Advanced Material Science 2010 we have published. And let us see what is the work was done by Dr. Prabhakar from KLE Belgaum, KLE Hubli. He initially started with like this. Then we have seen, we have published this work, and we have made the samples in corrugated structures. Then we have made the straight end, and we have evaluated the hardness properties, and we have seen that how strengthening effect on RCS versus rolling. When you do the conventional rolling, how it is different. And this work was published in Material Letters and Scripta Materia. And you can see that this is the way we have developed one RCS machine. Now we are having 2 RCS machines in NAL, and 1 RCS machine with different diameters, where we can put and do this work. It is basically installed in Basveswara Engineering College. This is the contributions made by Dr. S.A. Corey. You can see that the material can be, this is the material. I think what we have done is, for industrial practice, we require a large number of, so if you have a 12 by 12 diameter, or 10 by 10, or 8 by 8 with a lot of length of this material, we can easily process by taking this type of 2 HP motor. And you can see very nicely this is being processed, something like a sugarcane principle what we are using. Only thing, at 2 parts it will be corrugated, and after that it will become straightened. You can see that almost it became a straighten here. So this was developed and we have established in Basaveshwara Engineering College. So initially when we have done this work, we have done this. You can see that corrugated type of dies, and after that plain rollers are available. So when it comes to the material like this, so initially when you process this one, it will become corrugation. Then after that, we have calculated all the design properties and what is the angle of deformation it is taking place, all works we have done. And finally, we have made using a continuous RCS system. What we have made is, you can see that this is a guiding arrangement for specimen we have given, and these are the rollers, corrugated rollers, and we have the straight rollers also, that is plain rollers, where we have done extensive work on this one. Now you can see that after RCS aluminum copper system, why? Because aluminum, why we are using the aluminum 202420 with rotation and without rotation. These are the materials are extensively used for aerospace application. What is this WR is with rotation. With rotation means when the sample is rolled in this direction first, then it has to be shifted to another direction, and again we make it like this. So we are making a corrugation, we are making a plane. You are making a corrugation, we are making a straightening this thing. So we have done with 2024, 204 without rotation, with rotation, and by adding a scandium content, how it is influencing. If you talk about particularly of 367 to 470 MPa, that is ultimate strength has been increased by adding the scandium only. And if you see the as cast condition, it is 180 only. Almost it is double of this one after doing the RCS process. So yield strength is also substantially increased. Your hardness also is increased substantially. And one of my MTech student, S.C. Pandey, he has done this work and published in Material Science and Engineering A. I think we have done a lot of work on RCS. And let us come to the high pressure torsion of what material we are going to develop. And initially, you can see that it is like a coin type. It is a 10 mm diameter. You can see from here to here, it is a 10 mm diameter and 1 mm thickness. And after HPT, there are fin formation. Why? Because you are keeping this sample here and you are applying a lot of pressures like 5 GPa pressure, and you are rotating the bottom anvil so that the fin formation is there. You can remove this fin formation afterward. And when you wanted to evaluate the mechanical properties of such small samples, it is very difficult to make a tensile samples from here and find out your yield strength and UTS and percentage of elongation. So we can see the by doing the TM work, we can see the how the grain structure is changing, how mechanical properties are changing. This is the compact model. You can see that high pressure torsion, as I told, this is the machine which is established, which is installed in Basaveshwara Engineering College. I think one of the high pressure torsion facility. I don't know now how many people are working on high pressure torsion. But if you see this one, this is the bottom anvil. I think how many you can see here. This is the bottom anvil. This is the top anvil, and this is the plunger is coming and touching. We have kept the samples here, and you can see that slowly. If you see very carefully, this now it is started moving. This bottom anvil will move. I think if you see the close observation of this one, the bottom anvil starts rotating. Now you can see that one. The bottom anvil is started rotating, and you can take out after quarter rotation, half rotation, each number of samples, and this one complete rotation you can give, and you are applying such a high pressure for 5 GPa pressure you are applying by a plunger, where you can see that this is the top anvil and bottom anvil is here. This you can rotate very nicely. You can make up to 5 tons also. And what is happening is when you take such a material like aluminum 2 silicon and 0.25 silicon in as cast condition, and if you give different rotation, half rotation, quarter, 3/4 rotation, and 1 ton and 5 tons and 1 ton, how the hardness is changing. Why? Because you are having a 10 mm sample only, and from bottom you can see the distance from here to here, how the hardness is changing. This is more important. As you are going to the edge, there is a difference in the hardness values. It is improved hardness values are find out. And we have evaluated by using the ball indentation technique only, and you can see that how scandium is influencing and how aluminum 2 silicon. This is the basic study what we have done, and we have published this work also. And if you see that aluminum high pressure torsion of nanostructured aluminum alloys, how you can make after 2 tons, we have taken and did TM work. You can see that the almost after 5 tons, this is giving 0.15 micron. This is the average grain size with a lot of dislocation density. You can see that the here also after 2 tons aluminum 2 silicon alloy, how nicely you are getting a TM image. And what is the micromechanism substructure formation during HPT in aluminum 2 silicon alloy is similar to that of aluminum with dislocation cell formation and reasonable recovered substructure, and whereas aluminum 2 silicon and 0.25 scandium. Why? Because we have done almost a good amount of work on scandium additions. This is the 2 research projects we have completed with AICTE, and it is non-homogeneous, and they are array of non-equilibrium boundaries and dislocation tangles within the grains. These are the dislocation tangles. You can see very nicely these dislocation tangles can be observed. And Dr. Patil has done a lot of work on 7475 alloy. I think I take a 1 minute when he started this research work on high pressure torsion. What happened is I am one of the committee member for giving the research grants long back with BTU. And when we went, he was a special officer there, and he discussed with me that he has to take some research problem and wanted to do some good work on this one. That time, Professor Corey was the registrar. And when immediately it has come to my mind that after doing my postdoc at USA, we with our Professor T.G. Langdon, we have planned some work on aluminum 7075, 7475 alloys, 702024 alloys, that how this high pressure torsion is helpful, and we can do the work. So this immediately within I think 30 minutes or 45 minutes, whatever his research problem, why? Because everything was clear in my mind. I told Patil to I have dictated him, and he made within 30 minutes the research problem is made, and we could able to formulate the work what is expected. Why? Because that time all the samples whatever we have made, we have sent it to University of Southampton, UK, and we sent all the samples, but we have the initial microstructure, initial composition, everything we are having. And finally, after doing all the things, he had been to NML Jamshedpur to evaluate the mechanical properties. Then he has done extensive TM work, and finally we could able to make one good PhD thesis on high pressure torsion of different aerospace grade aluminum alloys. So what work he has done is commercial 7475 alloy he has taken, and after doing the for 2 tons, you can see that how the hardness is changing, and you can see very nicely that in as received condition it is the same, almost like Vickers hardness, micro hardness is around 160, 162 hardness, whereas you can see that that has been increased to 218, 220 microns at the edge of the samples. As from the center, as you are going to the edge, the hardness is improved as expected. And this is the average micro hardness values we have taken and presented here. Similarly, we have done the ball indentation technique on these things. Why? Because we should appreciate the contribution made by Dr. Gautam Das of NML Jamshedpur, where when any type of samples we are having, whether it is a metallic sample, polymer sample, or he has done extensive research work, he has patented his ball indentation technique equipment. He is supplied to 5 industries, including Bark. He has supplied these machines, where those who are using this ball indentation technique like a microscope only, you can see that by loading and unloading technique, you can evaluate the mechanical properties, and you can see that 7475, it is strength has come to almost like 1150 MPa, which has not been reported elsewhere after doing this, whether ultrafine grain structure, anything we did not find such type of 1100 MPa. That's what in aluminum alloys, getting this type of strength properties, not by the severe plastic deformation, using a high pressure torsion only is possible. And this is the work whatever done on 747 Li. I think if you see this one microstructural observation, before it is, if you see the grain size of this one 7475 Li, it is almost like 40 microns average grain size. We have done the optical microstructure and SCM microstructure, and this is the Deepak Patil, whatever he has published in Material Science in 2013. And this, from this, we, after doing the TM, detailed TM work, what we can see that a high pressure torsion, it introduces a significant grain refinement. High density of dislocations can be, you can see number of dislocations are more. There is a method to calculate the number of dislocations also. You can take 1 micron by 1 micron or 10 nanometer, 9 nanometer size and take the number of dislocations, and you can measure the dislocation density. This also work we have done, and most of the grain boundaries after 2 turns are ill-defined. These are all called ill-defined grain boundaries. Why? Because there is no particular grain boundary, and they correspond to non-equilibrium boundaries, and they are a characteristic microstructural features of material process. By whether you do any ECAP process or HPD process, you are going to have such a beautiful microstructures after TM studies. And some of the observations what we have made from 7475 is the hardness increases around the peripheries of the disc, but the values remains low in the central region. And after 2 tons, we have seen that maximum hardness we have achieved. Similarly, we have done for 2 tons, grain size is reduced from 40 microns to 70 nanometers. I think this obtaining a 70 nanometers by any severe plastic deformation except HPT is not possible. And you can see that UTS value of 1050 MPa in aluminum alloys, which is very significant, and you can see that at the edge we have observed after 2 tons was attained. This is the contributions we have made for 7475 Li. Now 7475 Li, why we have taken is after all aluminum alloys, if you are talking about the CPL 1000 series aluminum, 2000 series is aluminum copper system, aluminum manganese is 3000 series, and aluminum magnesium is 4000, aluminum magnesium silicon is 5000 series, aluminum 6000 series is aluminum silicon, 7000 is aluminum zinc magnesium, and 8000 is aluminum lithium alloys. So this is the main alloy. What earlier whatever we have studied 7475 alloy is a commercial grade aluminum alloy, that is high strength aluminum alloy. Out of all aluminum alloys, that is called high strength aluminum alloy. Initially we are taking that one alloy only style, and we have achieved 1050 MPa. Now this 2024 is a conventional material alloy which is used for almost all aerospace applications. Now this is being replaced with 5000 series aluminum alloys. Now you can see that as received conditions, you can see beautiful grain structure. And as I said that these are all at low magnification and high magnification. You can see that this is around 100 microns. So this will come around 25 microns. This is average grain size. If I take, it comes around 25 microns. So we have taken, why? Because duraluminum 2024 series is called duraluminum, where copper percentage will be 4.5%. This is not weldable material, and those who are the faculty members, I wanted to emphasize that there is nothing called non-weldable. There is no word called non-weldable. So people get confusion with what is this weldable and non-weldable. There is no question of non-weldable. This aluminum 2024 alloy also can be welded, but what we don't expect is we don't expect a desired mechanical property. So there is no use of doing the welding of these aluminum alloys. So we do different type of work, and we have initially you have seen quarter rotation, half rotation, 3/4 rotation, 1 rotation, 2 rotation, and 5 turns. These are number of turns we have given for aluminum 2024. This is the work done by Dr. Patil of KL Belgaum, and this is I have only guided, and most of the samples whatever he has taken to Jamshedpur, and he got all the properties. And you can see that at 5 tons of this aluminum 2024 alloy, 1160 MPa. This is what is expected. 1160 MPa he has achieved by doing this 5 tons HPT process. I think I will not take much details of, you can calculate the N value, K values also. And you can see that the strength values depending on number of tons. You can see that since it is a PhD work, we have done a detailed work on how it will changing number of tons as you are changing, how the strength is improving. Here you can see that from the center of the edge of the sample we have taken, as you are increasing the number of samples, it has almost achieved 1100 MPa. And this is what is the results from strength versus number of tons. And TM image at the 5 ton sample at the edge, what we wanted to, since we got a high UTS value, so we have taken that samples, we did a TM work, and this is, you can see that almost 15 mm is equivalent to 200 nanometers. So you can find out what is the average grain size here, and SADP pattern we have taken. And from this selected area diffraction pattern also we have taken, and what we are getting information is that nanostructure is possible on aluminum 2024 alloy after 5 tons, and what we have got is a UTS of 1160 MPa at the edge of the disc. This is the work we have done, and now I request somebody, after doing all these things, you are really showing that there is a tremendous improvement and improvement in the UTS value, and this is published in a peer-reviewed journals. It is not like that we have published in a conference paper or anything. And after doing this one, we thought that we'll submit a proposal to AIRDB and see that whether we can get funding. So we did, along with Professor S.A. Corey, we have submitted a proposal to AIRDB, and what we have done is, we have done the basic study where we have developed a machine and shown that this is where you can generate 1150 MPa UTS values of 1150 MPa by using the high pressure torsion. This is a basic research work we have done. But when we have presented this work to AIRDB, they are all metallurgy people and mechanical people. What they simply rejected this proposal. Why? Because they asked that where I can use this 10 mm in my aircraft system. So very difficult to realize what is the exact problem. So what we have done is, then we have taken a laser beam welding of skin materials. Why? Because these 2024 are aluminum magnesium scanning 5083 material. We have taken laser beaming. We can weld very nicely. Why? Because we can adapt fatigue work, and we can evaluate the corrosion behavior, all these things. Why? Because you have to talk about applied research. That is, fundamental research is accepted, but like AIRDB, they may not grant your AIRDB work for this one. Basic research work, if you want to apply, you can apply for AICTE, you can apply for DST, like that. Now IICTE director has become the secretary of DST now. I think there will be now CSR director is becoming a DST secretary is the first time. I think you can appreciate that there will be a lot of improvement. Why? Because he will understand some of the applied research also. Now, when you apply for the accepted research, applied research on laser beam, because we thought that this is not, they are not interested if you are talking about 10 mm sample. But if I talk about 2.5 meter by 4 meter, I can do the laser beam welding and I can evaluate all the mechanical properties. This took almost 1.5 years for understanding these things. Now we applied, we completed this project successfully. And after that, we wanted to see that really what are the problems the aerospace sector is looking. Then we submitted one problem of creep studies, which we can see on IN7, the Inconel alloy, nickel-based super alloys, and we have got around 1.8 crores now till 2024. 2024, we can work on this one. We are doing extensive work. We have created a creep facilities NAL. Those who are interested, they can use these facilities also. And after all, working for so many areas and developing a lot of aluminum alloys, what is you are expecting? What is the final output? What you are going to have? What you are having in your mind? That is most important. It is not the question of doing the research work in the laboratory and you get your PhD degree and forget about it. It is not the question. So finally, what your research area, now you can see that a supersonic passenger which goes at around 2200 kilometers per hour, 1.8 Mach, it has a windowless aircraft. You can see that there is no window here. You can see outside whatever is there. This is all possible with the graphene material, which I was explaining. You wanted to have a luxury life and you wanted to have it is economically, it should be viable. So for doing all these things, what type of materials are required? Everyday research work is being carried out. I think I would have talked more on this one. Let us see that the as application part in the starting slides. I think I have another 3 slides and another 15 minutes time is there. And if I see that what are the research work we are doing, whatever the aluminum alloys, these are all aluminum alloys only. Whatever you are talking, you should see that real part of, even if somebody comes to NAL, you can see the skeleton of what Saras aircraft we are making with aluminum 2014 and 2024 material. And what the people started using is from one corner of the globe to another corner of the globe, like USA to Australia, it takes almost like 17 hours travel time. This is what is expected. But people now, once you say that it is taking around 17 hours, people now they wanted, can we make it as 8 hours time? So that also people started using, and you have a double ducker aircraft system here like this. And what is expected is, now you see that the supersonic passenger aircrafts, they are going to start by 2029. We will be having, like United all the airlines have started their research work, and people have contributed particularly on aluminum alloys and fiber reinforced plastics. They have done a lot of work. And New York to London, it takes only 3.5 hours and 60,000 height. And as I said, from one corner of the globe to another corner, like USA to Australia, it can take only 8 hours journey, which is tremendously, we can make this research contribution. And this is expected by 2029, where we can one corner to another corner, you can travel in 8 hours journey only. Nowadays, whatever the amount of research work that is being carried out, earlier if you want to go from Bangalore to New York, you have to get down at Dubai, or you want to get down at Germany or London somewhere, and you have to go to New York. Nowadays, the facilities have come directly. You can fly to New York directly or Los Angeles. I think this is all possible. That's what the importance of the research work should be understood, and where to apply the projects also you should understand. And if you see this United Airlines, what they are going to, the velocities, if you see that miles per hour, almost like supersonic means it is 920 to 3000 miles per hour, which is more than sound speed. Sound speed generally it is around 760 meters per miles per hour. This is the speed, or 1482 kilometers per hour. This is the speed which is, it is supersonic aircrafts are available. Now we are trying to make supersonic passenger aircraft. Why? Because the sound issues are there. There are some issues which they have stopped. Now they have improved those things. I don't want to give more details. Some of the work they don't want to publish also, and they wanted to directly come to the application part. So I think if you see this one, the day it will come that whatever research work you are doing, it is going to implement in your life. And I think I have another 10 minutes. I think I'll complete by, this is the 59 slide. That is the last slide. What we can take away from this presentation is, I think you can do very good work on nanomaterials, and whatever work we have done on HPT should be now transferred to industries. And this subject is very important, and applied research is very much needed. After all, the basic research should be implemented somewhere. Unless you understand the basic research, you cannot do the applied research. Unless you have the applied research, you cannot do the basic research. So both are intersective nature. And try to understand the above and write research proposal as needed. I think when you write any research proposal for funding, I think you should able to convince the members that why it is useful. That's what application part is more important. And High pressure torsion is proved to obtain nanostructures in aluminum alloys. This has been proved, and where we got 1100 MPa. Now this has to be taken to industries. I think with this brief introduction about on aluminum alloys and its use for your application part, let me sincerely thank Dr. Raju for giving this opportunity, and all the delegates who are patiently listening for 1.5 hours. Thank you very much.
Uh, Thank you very much, sir.
I think
Dr.
people don't go
Venkateshwarlu,
very
sir.
deep.
Yes, sir. Thank you very much for your very informative and in-depth knowledge about HPT, RCS, equichannel angular pressing, which is a need of the hour.
Yeah,
I think we have been doing it only theoretical, as you told.
yeah,
We have to follow something called as a 4P or 5P model.
correct.
First of all, we have to see that we conceptualize a problem,
Yeah,
then make a problem into a project into a what we call patent,
yeah,
right? Then patent into a product.
yeah, correct.
So that's what we have to do. I think probably you have done a lot of work in that, and you have received a lot of patent, and you have made practical application of what research you have done. So most of our academicians, what we lag is basically, as you told, we don't make a product. We restrict
Yeah,
our research only to academics.
yeah, that's
So
right.
it is not fruitful in a sense. You are rightly mentioned. I think we will take your words very seriously, and
Yeah,
I request all my colleagues who are on this meeting platform to take Venkateshwarlu sir's advice very seriously and make our sincere effort to convert our academic research into products, so that we can strengthen, and as far as our nation goes, make in India, so that we can be self-reliable and self-sustainable. So
100%.
even for a small LED, we are dependent on neighboring countries, which should
Yeah,
be very much reduced in the sense. So in that sense, you have given a wonderful lecture, sir.
yeah,
Thank you very much. At the outset, I would like to thank you on behalf of the management and Dr. Ambedkar Institute of Technology and Department of Mechanical Engineering for giving such a nice technical talk, and also sharing us the knowledge of grain refinement. In fact, when you are telling about one of the Bible paper on grain refinement, I remember my PhD days, where I
yeah.
have said that I think 25 to 45 pages of a
Correct.
paper which have been written on grain refinement of aluminium by
Yeah,
Professor Murthy and Chakraborty
yeah.
of IIT Kharagpur, and Professor Murthy of IIT Madras, now who is director
IIT
of
Hyderabad.
IIT Hyderabad. Wonderful paper. As you told, rightly mentioned, it is a Bible for grain refinement. And
Correct.
everybody who is working on aluminum alloys should read that paper.
Correct.
That gives very good insight about grain refinement.
I
Once
think you
again,
can see
thanking.
here
Yes,
Nano
yes, sir.
SPD program where my host for postdoc, Professor Langdon, is sitting here, and
Okay, sir. Okay.
Rolson Value, who is the pioneer in severe plastic
Severe
deformation,
plastic deformation. Yes, sir. Yes,
and
sir.
you can see that I am sitting at the one of the
Corner. Yes, sir. Yes, sir. Left side corner.
Yeah.
Very nice. Very nice to see you, sir.
Thank
Thank
you
you
very
very
much.
much, sir. Thank you very much for giving a wonderful talk, sir. We'll meet you for our further research work, sir.
Yeah. Please. Huh? And
Okay,
if you
sir.
have any queries, candidates can approach this email. Otherwise, they can directly talk
Yeah,
to
if
me.
anybody have any queries, you can ask sir now also, or you can contact him through mail.
Yeah.
Should I ask a question,
Yeah,
sir?
yes,
Yes,
sir.
yes,
Very
please,
well, sir.
please.
Pankaj, sir.
Myself, Dr. Pankaj Kumar Singh from IIT BHU.
Sir.
Your presentation was very nice.
Sir.
Regarding the iron research, what you are mentioning, if any, we are doing some research work on the iron, there is a very big problem of the rusting problem.
Yeah.
Then can you suggest any method so that we can rectify that problem in doing the synthesis process like the calcination or sintering process? How we can do that thing? Thank you.
Sir, you are talking about ferrous alloys. I discussed everything on non-ferrous alloys. We are particularly on aluminum alloys, where you can see that oxygen is reacted with aluminum, and there is always a alumina layer will be there on all aluminum alloys. I think what is required in iron-based alloys is you have to have low carbon content where you can make corrosive anti-corrosion properties.
No, but what basic process, what we can put in our methodology?
That is, you can go for, suppose any material is there, you can go for the coating technologies. Nowadays, plenty of coating technologies are available. That
No,
is,
coating, after coating, you can't do the calcination and sintering process, sir. I want the basic process, how we can move the process.
iron material, I don't have much idea, sir.
Okay, thank you.
Thank you, thank you.
I think professor was asking in the last meeting also, one of the question was all about calcination. He asked me about the temperature. Sir, I told you asked about the sintering temperature and calcination temperature. Usually calcination temperature, what I read was below 1000 and 1100 degrees centigrade. And whereas your sintering temperature basically depends upon your melting point, around 0.75 to zero point 0.8 times. And if you are looking at recrystallization temperature, it will be around zero point 0.3 to 0.4 times the melting point. But since we are not much into iron, probably we may not, but I will get back to you, sir. As you are rightly mentioned, I will research and get back to you surely, sir. Pankaj, sir.
Yes, yes, sir. Thank you.
In which area you are working, sir? May I know in which area you are working, sir?
Actually, my work is related to bio ceramic and the
Okay, sir. Okay, okay.
nanoparticles, that
Okay.
way of research I'm doing.
Okay. Means, shall I give you an opportunity to talk in the afternoon for you, sir? You can talk for half an
Def-
hour on
def-
your research work if you wish.
def- Definitely, sir. Definitely. You are welcome.
Yeah, then I will send you the meeting, the same link you can use. And 2:30, half an hour you can share. I will share my experiences half an hour, sir.
Okay, okay. Sure, sir. Sure.
Okay, sir.
I will wait.
Then 2:30 we will meet, sir.
Okay, okay, okay. Thank you.
Okay, sir. Thank you. Thank you, Pankaj, sir.
Sir, good morning, sir. Raju, sir.
Yeah, Kirti, you can ask your question to sir.
Sir, I do not have any question, but I have a compliment.
Ah, tell me, sir.
Whatever Venkateshwara sir said, we
Ah,
enjoyed 1.5 hour lecture.
yes, sir.
And
Yes,
that
sir.
last
Yes.
5 minutes, what conclusion you gave?
Ah.
It is a what cherry on the cake, sir.
Okay.
Such a beautiful concluding remark of the talk. I didn't see anywhere. Just
Okay.
to appreciate you people and your arrangement, sir. Thank you.
Thank you. Thank
ನನಗೆ
you.
ಬಹಳ
Thank
ಖುಷಿ
you.
ಆಯ್ತು ಸರ್ ನಿಮ್ಮ ಮಾತುಗಳನ್ನು ಕೇಳಿ. Thank you.
Thank you, sir. Thank you very much, sir. Sir, tell me, sir. Venkateshwarlu, sir.
This is fine. I think it is almost I have taken 1.5 hour. I
Yes,
think
sir. Yes,
people
sir.
must be getting bored.
No,
What
no,
is
no, sir. It was very, very interesting. In fact, I was also looking at high pressure torsion and RCS method, but it was very nice talk as far as academic is concerned. It was really wonderful, sir.
Yeah,
Thank you very much, sir.
we are going to help for anyone who is interested to take this type of work.
Yes, sir. Yes. Because I was suffering in CNT based carbon nanotube reinforced aluminum composites, where for sintering itself we were suffering. I think these kind of methods will help us in realizing a very ultra fine grains
Yeah,
for our products. Thank you, sir. Thank you, sir. Sir,
Thank you.
shall we leave, sir? In that case, if no questions
Yeah.
are there,
Can I
and
leave?
everybody is giving good feedback that your talk was very good. Thank you. Thank you, sir.
Thank you very much, Dr. Raju.
Okay, sir. Okay, sir. Thank you. We will join. Feedback is shared, my dear participants. Feedback is shared in the chat box. Please, we'll also share it in the WhatsApp group. You can please fill the feedback, and we'll join again at 11:30. Dr. Tomagna Chakravarti from IIT Patna will be delivering his lecture. Thank you.
Thank you.
Yeah, I have unmuted. Okay, so let me share the screen then. Okay. Yeah, yeah. Sure, no problem. Yeah. Is the screen visible?
Yes, sir, it is visible. Make it full screen, sir.
Okay, just a minute. Yeah,
Yeah. Can you change the slide, sir? 1, 2, 3, like that. Whether it is going to
yeah,
change.
sure.
Yeah, yeah, it's changing, sir. Okay, no problem. Sir, the
It's okay.
session will
Okay,
start exactly at 11:30, sir.
no problem. Okay.
Yes, okay.
Sir, good morning, sir. Tomanga Chakravarti, sir.
Yeah, good morning.
Yeah, are you online now, sir? Shall we start, sir? It is exactly
Yeah.
11:30.
Oh, okay. So shall I start?
Yes, sir. I'll just introduce you to the audience, then you can start, sir. Huh?
Okay. No problem.
Yeah, we'll read your biodata, give you a brief account of your work and all, and then we will start.
Okay, no problem.
Thank you very much, sir, for accepting our invitation to deliver the lecture in this faculty development program. And your topic rightly suits our FDP also. And we are very glad that you accepted our invitation to give the expert lecture. Now I request my dear colleague, Mr. Baire Gowda, to introduce the speaker to the audience. Over to you, Baire Gowda.
Yes, sir. Okay, welcome all the participants and the speaker, Dr. Chakrabarti, Tamogna Chakrabarti. And I'm going to give a brief introduction about Dr. Tamogna Chakrabarti. He is an assistant professor, Department of Metallurgical and Materials Engineering, Indian Institute of Technology, Patna. And his research interests are processing, sintering, characterization, and mechanical behavior of ceramics, UHTCs, computational modeling of sintering, and related phenomena. Phase field modeling study of microstructural evolution in phase transformations, and is having professional experience as assistant professor in Indian Institute of Technology, Patna from March 2018 to present, and DST Inspire faculty, Indian Institute of Technology, Kanpur, India, October 2017 to February 2018. Postdoctoral fellow, Colorado School of Mines, US, September 2015, March to 2017. Assistant Design Engineer, Mecon Limited, Ranchi, June 2007 to July 2008. And when it comes to education, PhD from Indian Institute of Science, Bangalore, India, and the thesis title is a Study on Reactive Hard Processing of Zirconium Carbide, and under the advisor of Professor Vikram Jairam, Materials Engineering, and the area of study is ceramics processing, ultra high temperature ceramics, reactive hard processing, pressing, sintering, computational modeling of reactive hard pressing, mechanical characterization through nano indentation, phase identification through SEM, EPMA, XRD, and retrieved analysis and thermal analysis. And he has done his BTech in Government College of Engineering and Ceramic Technology, West Bengal University of Technology, Kolkata. And his experimental skills include MRF vacuum arts press, thermoline furnaces, scanning electron microscopy, EPMA, XRD, and TGDTA, Raman spectroscopy, optical microscope, practical size analyzer, nano indentation, CSM micro indentation, Instron UTM, acoustic measurement. And computational skills are phase field modeling, C Julia programming language, finite element analysis using Abacus and calculus software, MATLAB, Maple, Mod, and foolproof for retrieved analysis, ImageJ, Adobe, Photoshop, AutoCAD, and LaTeX. And he has done 9 papers publications, and having citations of 437, H index of 5, and I-10 index of 4. And some of the awards and grants he got are a recipient of Inspire Faculty Award 2017, Department of Science and Technology, Government of India. Recipient of CSIR International Travel Grant in the year 2011. MHRD as a Senior Research Fellow Scholarship for pursuing PhD at IISc Bangalore 2008. And he has done some research experience, having some research experience on study on reactive hard pressing of zirconium carbide, reactive hard pressing of zirconium carbide, effect of transient phases and reaction on densification, low temperature reactive hard pressing of zirconium carbide, modeling of reactive hard pressing. Uh, I welcome you, Dr. Chakrabarti sir, for the topic ultra fast sintering of nanoceramics through flash sintering. I welcome you, sir, once again.
Okay, thanks a lot. Thanks a lot for your kind introduction.
Yeah.
And first of all, I must thank the organizer of this webinar, Recent Advances in Composites and Nanomaterials. And also, I must thank Dr. Raju for giving me this opportunity to speak in this. Okay, so with that, let me start with today's talk. And the topic of today's presentation is ultra-fast sintering of nanoceramics through flash sintering. So before going into the topic, let me briefly say something about ceramic materials, ceramic processing. Then I will slowly introduce you into to the topic of flash sintering and ultra fast sintering of ceramic materials. Okay, so let us start with a little bit of introduction of ceramics, even though I think most of you are quite familiar with it. So I'm not going to spend too much time on this. So ceramic materials are the oldest man-made materials. So oldest in terms of like clay potteries. So clay potteries are the oldest man-made materials which were made, I think, more than 50,000 years ago, even older than that. And clay figurines, so figurines made out of fired clay, those are also like very old. Some of the examples have been found are 30,000 years old and so on. So ceramic materials are definitely the oldest man-made materials, and the reasons why they are oldest man-made material is that so ceramic materials are basically the oxides, nitrides, carbides, and so on. So oxide means metal oxides, metal carbides, metal nitrides, and so on. So and metal oxides are the most common compositions of the earth crust. So earth crust, if you think about it, it's made up of silica, alumina, mostly silica, alumina, and MgO. So these three are also very prominent ceramic materials. So because of the abundance of the ceramics readily available on the earth crust, so ceramic materials were actually the oldest man-made materials. So now if we come to the definition of ceramics, so ceramics are defined as inorganic non-metallic materials. So they are inorganic and they are non-metallic. So the examples are just, I told you, it's the oxides. For example, oxides of silicon, that is silica, oxides of aluminium, that is alumina, oxide of magnesium, MgO, and not only it is limited to oxides, it's similarly silicon carbide, silicon nitride, zirconium carbide, titanium carbide, all these materials, all these oxide and carbides and nitrides of metals, they are defined as ceramic materials. Now, the total gamut of ceramic materials are nowadays subdivided into traditional ceramics and advanced ceramics. So traditional ceramics are those which were like old ceramic materials which we are making for thousands of years. So those are the traditional ceramics. And advanced ceramics are defined as those ceramic materials which we have invented or discovered in the last, let's say, 50 to 100 years. So those are defined as the advanced ceramic materials. So here we in this slide, we have examples of both traditional ceramic materials and advanced ceramic materials. So let me start with the example of traditional ceramic materials. One such example is the the Ming Dynasty bowl, which was made in 14th century. So it's like 600 years old, more than 600 years old. And in fact, this is an interesting fact. So most of the traditional ceramics, the Chinese were the masters of the making ceramics materials. So many of the traditional ceramics are actually invented by the Chinese. For example, porcelain. We all know about bone china. Those materials were all developed in China. So this bone china and the porcelains are examples of traditional ceramics, but traditional ceramics are not limited to that. So tiles, for example, is also another example of traditional ceramics. So this is another example of tiles. This is from Alhambra Palace in Granada, Spain. This is the intricate design tiles, which is again a ceramic material. So if you think about the traditional ceramic materials like porcelain or tiles, or even the common ceramic materials that we use, for example, the sanitary wares. So these traditional ceramics are all made up from clay. some percentage of clay. So traditional ceramics are generally made from clay. So now if we come to our advanced ceramics, so advanced ceramics are generally not made up from clay. So there are many examples of advanced ceramics. Some of them I'm showing in this particular slides. So one such example is the refractory bricks. So refractory bricks are made from many different materials. So here they are made from MgO. Another example I'm showing you, the electric fuses. They also use some non-linear conductor or varistor materials. They are mostly some kind of oxide ceramics. And so, so this is an electronic examples of advanced ceramic materials, but advanced ceramic materials are also used in many other electrical applications. For example, capacitors. Many capacitors are made up of ceramic materials. So ceramic capacitors, they're called. They're made up of barium titanate and many other materials. Ceramic materials are also used for making piezoelectric materials, for examples in ultrasonic machines and so on. So they are made up of, I think, PZT. So that is lead zirconia titanate and other ceramic materials. So these are electrical applications. If you think about the mechanical applications, so ceramic materials are very typically they have very high melting points. So they are used for high temperature applications, for example, gas turbine blades. So this is one such examples. This is silicon nitride, Si3 and 4. This is also a very high temperature ceramic materials, and they are used in making some gas turbine rotor. So typically not in electricity generations or large size turbine blades are not made from this. But these are typically used for in engines, for example, in this turbo engines. So there we use the silicon nitride, the turbine rotor. And another example I'm showing here is tungsten carbide. It's again, it's a carbide and also a ceramic materials. So these are also used for high temperature applications. So we can see that ceramic materials are used for many different applications, ranging from traditional ceramic, advanced ceramics, and in advanced ceramic also many different applications: electrical applications, refractory applications, structural applications, and many more. Now, if we think about the processing of ceramic, so how we make any ceramic materials. So this is kind of interesting because ceramic materials are made in different ways from the most metallic materials. So metallic materials, if you think about it, any metallic materials, this can be a steel bowl, or it can be a steel rebar, or any other aluminum brackets which we used in normal practice. Most metals are made from two processing. One is casting, and second is the plastic forming. So most metals that we use nowadays are made from these two process: the casting or metal forming, or in a combinations of casting and metal forming. But those techniques cannot be used for making ceramic materials. The reason is that the ceramics have very high melting point. Most ceramics materials have very high melting point. For example, alumina has a melting point of 2000 degrees centigrade, zirconia having around 2700 degrees centigrade. These are very common ceramics. Silica is another ceramic materials. Its melting point of 1700 degrees centigrade. And these are oxides. If we go to carbides, the melting point is even higher. For example, hafnium carbide melting point is beyond 3500 degrees centigrade. Zirconium carbide is also 3500 degrees centigrade. Titanium carbide has a melting point of 3000 degrees centigrade. So they are very high melting point materials. In fact, they are these carbides which are having higher than 3000 degrees centigrade melting points. They are called ultra high temperature ceramics, or UHTCs. So, so we can see that typically the ceramics have much higher melting points. So just to give in comparisons, Aluminium have a melting point of 600 degrees centigrade. Gold is having around 1000 degrees centigrade. Copper is around 1000 degrees centigrade. So aluminum, gold, copper, they are 600 to 1000 degrees centigrade. Steel is slightly higher, iron 1500 degrees centigrade. But if you compare that with ceramics, for example, alumina to 1000 degrees centigrade. Okay, so silicon carbide doesn't melt, but it dissociates at, I think, 2500 and beyond degrees centigrade. So it's much higher than the metals. So because they are having such a high melting point, we cannot really use casting process to make ceramic products. So that is completely not possible. Now, plastic forming is another technique we use, for example, rolling, forging, extrusions for making metal products, which we again cannot use for ceramics because ceramic materials are by nature very brittle. They don't have much plasticity. So we cannot do any plastic forming either for making ceramic materials. So these two processes are completely not feasible. So then what is the technique that we use to make ceramic? That the process that we use is the powder processing technique, so which I will explain in the next slides. So, so ceramic materials we make by powder processing. Now, what are the microstructural features that we need in the ceramic materials? So, to achieve high strength in ceramic materials, we need small grain size and uniform microstructure and the material free of flaws. So they are not too much different from metals. If in metals also, if you want high strength, you need small grain size and flaw free. So ceramics are also similar in that regard. If you think about high toughness, again, you need duplex microstructure with high aspect ratio. For high creep resistance, here we require actually large grain size rather than small grain size. So this is again same for the metals. For metals also, if we need high creep resistance, we generally require high grains, large grain size. Sometimes we make single crystals without grains or without grain boundaries rather. So, so they are similar. But what we can conclude is that for making a strong, tough ceramic, we need high relative density. Okay, so to conclude here from this slide, so ceramic materials cannot be made by melting or plastic forming. So casting or plastic forming is not possible. So we use powder processing to make ceramics, but also to achieve high strength, toughness, and so on, we also need high relative density. Okay, so now the question is how ceramics are made. So ceramics are made from powders. So we start with powders of ceramic. For example, if you want to make a alumina piece, we will start with alumina powder. Okay, so that is why ceramic processing is generally is also powder processing. So one thing I just briefly mentioned is that some metals also behave like ceramics. Some metals are also having very high melting points and very low plasticity, for example, tungsten. So for those metals also, we use powder processing technique to make a product. So that is called the powder metallurgy. So ceramic processing is very similar to powder metallurgy process. We start with the powders. So starting with the powders is also easy for ceramics because it's inherently brittle. So you can crush any raw materials to make powders. So so we start with the powders. Then with the in the powders we add binders. Binders is added to achieve the green strength so that we can handle the powder piece, and then this powder are shaped by two different techniques. Either we use some kind of a slip casting or we use a die pressing. So either slip casting or die pressing to get the final shape, whatever shape we want to make. And after the shaping process, we put the piece into a furnace, which is called the sintering process to make the final product. Now there are there can be two questions here is, so if we start with powders and then press the powders into a shape, whatever the final shape we wanted. For example, if we want to make this turbine blade, we start with silicon nitride powder in theory, and then we can use a die to make the particular shape of this particular rotor, for example. So the question is, why do we need to put into a furnace and heat it to high temperature? The reason is that, as I mentioned in the previous slide, so to achieve high strength and high toughness, we need very high density. That means very low porosity. And if we don't do this sintering step, the material will remain very, very porous, and it will not have any strength at all. So material before the sintering step will behave similar to a chalk. So I think everybody is familiar with chalk. So it will be like chalks. It will not have any strength at all. So the strength is achieved by this sintering process, where we keep that ceramic part inside a furnace. So this sintering step is the most vital step for any ceramic process. Now the next question will be, like, if you start with powder and you apply pressure inside a press, why can't you achieve very high density, right? So why can't we achieve very high density by just pressing at room temperature, by applying, let's say, very high pressure? So the problem is, the ceramics are very hard materials, so there will not be any plastic deformations at all. So this is one problem. And secondly, if we take, let's say, powders, and so powders, if we think about it, we can imagine the powders as each grain of powder as a spherical ball. If we imagine like that, ideally, and if you take a spherical balls and if you pack them together, so maximum packing density that you can achieve is a 74%, right? That is a cubic close pack or hexagonal close pack. If you do, the maximum packing fraction that you can achieve is 74%. If all the particles are spherical and they are of the same size, so that means there will be around 26% of porosities. But that is in the ideal case, if the powders are arranged in a periodical manner in case of a cubic close pack or a hexagonal close pack. But in practice, the powders will never be arranged in such a periodic manner. So they will be arranged some kind of a random close pack. And people have done calculations, and with random close packing, the maximum packing fractions that you can achieve is around 65%, 66%. So maximum relative density that you can achieve by pressing ceramic powders at room temperature is the 66%. That is you can say the theoretical limit. And if the powders have no plastic deformation, and they generally do not have any plastic deformations, so that is a theoretical limit is of around 66%. That is what you can achieve by just pressing ceramic powders. But in practice, we generally get something between 50 to 60% by powder pressing. So the material is only 50 to 60% dense. That means it contains 50 to 40% of porosities. And that's why the material will behave just like a chalk, and it will not have any strength. And that is why you have to put the material into a furnace to densify the material. And this densification process is called sintering. And that's why sintering is very important step for making any ceramic materials. Okay, so let's now go into definitions of sintering process and so on. So sintering is a process defined as by which powder compact is transformed to a strong dense ceramic body upon heating. So just exactly I mentioned. So if you have a powder compact, that is the green material after pressing. So the green material after pressing, and we put it into the furnace for the sintering process. So sintering transform the powder compact into a strong dense ceramic body upon heating. So that is the sintering process. And this is the heart of ceramic processing. So sintering is the most important step for making any ceramic material. Now, what is the goal of sintering process? The goal of sintering process is to obtain theoretical density at lowest possible temperature. So there are two things. First is to achieve theoretical density. Second is at lowest possible temperature. So why close to theoretical density? It is because of this requirement which I mentioned, is to achieve high strength and toughness. We of course want any product to have high strength and toughness regardless what is the applications. We do not want a very brittle material. It's not very useful for any purpose. So we need to achieve theoretical density as much close to theoretical density as possible. So as little porosity as possible. And now why lowest possible temperature? So lowest possible temperature is because ceramic sintering process in typical ceramics requires very high temperature. And why high temperature? Because sintering process is a mass transfer process. So where we are eliminating the pores, that means we are filling the pores with materials. So material has to flow into the pores. So material can only flow and fill up the pores through the process of diffusion. And diffusion in these ceramic materials is very slow. And why diffusion is slow? Because diffusion is a thermally activated process, and it depends upon the melting point of a material. It scales very well with the melting point. So because the ceramic materials have very high melting point, so the diffusion process is also slower, because diffusion is like inversely proportional to the melting point. So to achieve significant densifications, to achieve significant amount of diffusion through the material, to complete the densification process, you have to raise the material to pretty high temperature. So how high temperature? So typically sintering is done from 0.5 tm, so 0.5 of melting point to 0.75 of the melting point. That is the typical requirement for the sintering. And this is like melting point in Kelvin scale, by the way. And so, for example, if we think about our example of alumina, so alumina has a melting point of 2000 degrees centigrade. So generally you need around 1000 to 1500 degrees centigrade for sintering alumina piece, and in practice it requires around 1500 degrees centigrade. So 2/3 of the melting point, even more than that, is required to sinter the material. So sintering requires pretty high temperature for most ceramics, because ceramics have very high melting point. So because we require very high temperature, so it is a very energy intensive process. So energy intensive process means you require a lot of energy, and because you need a lot of energy, you have to invest a lot of money. So in fact, so 30 to 50% of the cost of making a ceramic comes from the sintering process itself. So sintering process is very costly. So if we can manipulate the material or the process such a way that if we can reduce the sintering temperature, that will result into huge cost saving. So that is why the goal is always to obtain theoretical density at lowest possible temperature. Lowest possible temperature is to save energy and save cost. So that is the goal of sintering process. Now, what is the difficulty? So why sintering is difficult? So sintering is difficult because the driving force of sintering process is very low. This is in the order of few joules per mole. And because this driving force is very low, it's a difficult process. So for an example, a chemical reactions typically have a driving force of few kilojoules per mole, whereas the typical driving force for sintering is few joules per mole. So it is 1000 times less compared to a chemical reaction. So that makes the sintering process very difficult. Okay, so so now let's think about the driving force of sintering. What is the driving force of sintering? So I mentioned it is very low, but why it is very low and so on. So so now let's think about the driving force of sintering. So in previously, what I have mentioned here is that we take for making a ceramic, we start with the powders. So we press the powder into the final shape and put it into a furnace. So the material before sintering, we can imagine it is only 50% dense. So it contains 50% of porosities. And if we put it into the furnace, raise the temperature, at high temperature, material densify, right? So the pores gets eliminated. But the question is why pores will get eliminated if we increase the temperature, right? What is actually going on? Why there will be any densification at all? Why the pores will be driven out if we take the green piece, which is 50% densified inside a furnace? The answer is the reduction in the surface area. So what do I mean by reduction in surface area? So if you think about the particles itself, each particles have surfaces, and surfaces are defects. And why surfaces have defects? Because at the surface, the bonds are incomplete. Because the bonds are incomplete or dangling, it has excess energies. So surfaces are defects, and the system would always like to reduce the energy of the system. So how it can reduce the energy of the system? That by eliminating the surfaces. And this elimination of surfaces is actually what is driving the sintering process. So we can say that the driving force of sintering is reduction of surface area. So how the surface area is reduced by the sintering process? So it's pretty simple. So if you think about the hypothetical picture of sintering, so we have a particle assembly here. So each particles have surfaces. Now, if we take these particles and join them together, we are actually eliminating the surfaces and we are actually producing the grain boundaries. So when the particles are come close to each other and touch each other, the surface gets eliminated, and what is forming is the grain boundary. And generally grain boundary is having lower energy compared to the surfaces. So if we can replace the surfaces by the grain boundaries, we are actually gaining some energy. And this gaining of energy is driving the sintering process. But you might ask, is it always true that surfaces have higher energy than the grain boundaries? It did not be. So there is also another factor. If two particles are coming close to each other and touching each other, they are eliminating the surfaces and forming grain boundaries. So if you think about it, we are actually replacing two surfaces by one grain boundaries, right? So previously there were two surfaces, but when the particles are coming together and joining, we are only forming one grain boundary. So two surfaces are replaced by one grain boundaries. So this is always energetically favorable, and that is what is driving the sintering process. So when I mentioned that if you have a porous material and you put it in the furnace and you increase the furnace temperature to a pretty high level where the diffusion can happen significantly, then that will lead to densifications. And that is what is driving the sintering process. So, but now you might ask then, the sintering is very simple then, right? We have a powder compact, which is porous, lot of surfaces. We put it into inside a furnace, raise the temperature, surface are eliminated by forming grain boundaries, and material is densified, and end of the story. Very simple. There are no challenges at all. But the situation is not so simple, unfortunately, for us, because the system can reduce its energy by another way, not by bringing the particles together and forming grain boundaries. It can also reduce the surface area by simply the coarsening process or Oswald ripening process. So in Oswald ripening process, the pores doesn't get eliminated. What happens is that the small particles are gobbled up by larger particles. So larger particles grows and smaller particles shrinks. So number of particles get reduced and we end up with the larger particles, but no more densifications. So only the smaller particles becomes larger particles. By that process, we are reducing surface area and surface energies, but we are not getting any densification process. So this is called coarsening process, and this coarsening process also can happen in parallel with the densification process, and that makes the sintering very difficult and critical, because both processes can happen in parallel. So depending on your process temperature, powder quality, and many other factors, either you're going to get densifications, that is elimination of porosities and formation of grain boundaries, or you can get Oswald ripening and coarsening, so no densifications. And that is why sintering is difficult. And also, if you think about it, the driving force was very small to begin with. So combinations of this fact makes sintering a difficult propositions. So here, one more thing I want to mention before moving on. That factor is that so smaller is the particle size, smaller is the particle size, that is the starting particle size. Larger will be the surfaces or specific surfaces area, and larger will be the driving force of sintering. So if you use a smaller particle size, it helps in the densification process. So nano-sized particles are easier to densify compared to micron-sized particles because of the same fact that driving force is larger. So this is something critical. We will come back to that in future slides once more. Okay, so now, so just what I have mentioned is shown here, that so during the sintering process, there are different trajectories the system can follow. So these trajectories are shown here by these diagrams. If I can switch on this
Excuse me,
highlighter, yeah.
please hide this Google Meet link. Hide that
Yeah.
portion. There is hide
Yeah.
option. Yes, thank
Yeah.
you.
Okay, no problem. Okay, so so if you think about this, trajectories are shown here in this diagram. So on the x-axis we have percent theoretical density, and the y-axis we have the grain size. So during sintering process, if there are no densifications and only coarsening, so what we will see is the increase in the grain size but no densifications. So this is shown by the trajectory x, right? So here there are no densifications, only increase in grain size, so pure coarsening. So this is very bad, and this trajectory is shown by the trajectory x. Now, it's possible that during the sintering process, there is both coarsening and densifications. So both increase in the relative density, theoretical density, and also increase in the grain size. This is shown by trajectory y. So trajectory y is also far from ideal, because you will end up with a material with much lower than the theoretical density, which is not ideal. So what we actually want is the trajectory z, where we densify the materials to very close to theoretical density, and only after that the grain growth happens. So this is the ideal trajectory. This is shown by the trajectory z. Okay, so this is the trajectory we want to follow, but if we are not careful, our particle compact might get into the trajectory x or trajectory y, and we will end up with a suboptimal material. So this is the critical factor in the sintering process. Okay, so now, so I have already mentioned about the driving force of sintering is the reduction in the surface area and so on, but that is in the global scale. But in the local scale, what happens is shown here. This is the mechanism of sintering, the atomistic mechanisms of sintering. So if you think about atomistically what happens during the sintering process, this is shown here. So if you think about any surfaces, the surface can be flat, which is shown here by P2, or the surface can be convex, which is shown by P3, or the surface can be concave, which is shown by P1. So these are the three possibilities of the surfaces. Now, so from which surface to which surface the atoms will migrate, right? If the question is from which surface to which surface the atom will migrate. And this is what this hypothetical picture is all about, because sintering is a process where the atoms move to eliminate the pores, right? So, so if you think about the convex surface here, if this particular atom, if you think about this atom is only connected to one atom, right? So this atom is only connected to one atom in convex surface. So if you think about a flat surface, the surface atom is actually connected to two atoms, right? Two atoms. And if you think about a concave surface, the surface atom is actually connected to three atoms. So we see here, because of the curvature of the surfaces, the convex surface, the atoms are much loosely bound compared to flat surface or concave surface. So this atom is actually easier to remove compared to the flat surface or concave surface. Because in the convex surface, the atoms are easier to move because they are loosely attached. It's more likely that atoms will get detached from the convex surface and it will like to sit on the concave surface, right? So naturally, if you have surfaces of different curvatures, there will be an atomic flow from the convex surface to concave surface. Okay, so this is actually what drives the sintering process atomistically. Okay, but that is not the all. So this process, the detachment of atoms and then reprecipitations of the atoms, so this is called evaporations, condensations process. This is also one of the mechanisms of sintering process. But there is one more thing that we have to consider is the movement of the vacancies. Movement of the vacancies. So if you think about now vacancies, to create a vacancy, you have to take an atom from the bulk and put it on the surface. And if you do that, there will be vacancies created. For example, if you look at this black atom here. So this black atom initially was attached to four atoms, right? And if we take this atom and put it on the top of the surface or at the top surface in case of convex curvature, how many bonds we are breaking is 4 minus 1, 3 bonds we have to break, right? 3 bonds we have to break to create a vacancy in case of a convex surface. Now, if we come back to concave surface, if you do the similar exercise, you take this particular atom and put it on the surface, we are actually breaking one bond because initially this atom was attached to four other atoms, so four bonds. And if you put it on the top surface, it's still attached to three atoms. So only one bonds we have to break. So we can see here, it is easier to create a vacancy under a concave surface compared to a convex surface because we have to break less number of bonds. So the vacancy concentrations under a concave surface is always higher than a concave surface. So naturally, there will be a concentration gradient in the vacancy. So vacancy concentration gradient between a concave surface and a convex surface. So naturally, vacancies will flow from the concave surface to convex surface. So vacancy migrations we can imagine as the reversal of atom migration. So atoms will migrate from the convex surface to concave surface. So these two process actually drives the sintering process. And this can be explained through Gibbs-Thompson equation, which is shown here. I'm not going into that today because we don't have time for that. But this is actually the driving force of the sintering in the atomic scale. Now, if we think about the mechanisms of sintering, so this is the picture we always encounter. So we take an assembly of 4 particles. So this is an hypothetical picture. We have 4 particles and we can see that in between particles there are porosities, right? And these porosities we have to remove to densify the material. And how can we remove these porosities? These porosities can be removed by the diffusional processes, and these diffusional processes are essential for the sintering. And why this process will happen? This will happen due to the curvatures, which I have explained in the previous slides. So now if you think about these curvatures, which curvature will be created where? So where everywhere in the particles these are the convex surface, right? Spherical particles, everywhere there is a convex surface, right? Convex surface. But where the particles are touching each other, here we can see that here it forms a concave surface, right? So everywhere there is convex surface, but only where the particles are touching each other, they are creating a concave surface. And as I mentioned, naturally there will be the atoms are loosely attached at the convex surface compared to concave surface, so they will try to get detached. They will detach easily here, and then they will get attached here easily. So there will be a mass flow from the convex surface to the convex surface. And if you think about the vacancies, the vacancy concentrations are higher under the concave surface. So vacancies will move from this concave surface to convex surface. So material will move in the other way around, from the convex surface to the concave surface. And how the vacancies can move? They can move through diffusional processes, and there are many possibilities. For example, they can move through surface diffusions, where the diffusion only happens to the surface of the material, or they can move through the lattice diffusions, where from the surface the atoms move through the bulk of the material through diffusional process. So this is called lattice diffusion process. Or they can move through vapor transport, which is the evaporation condensation. So atoms get evaporated from here and then get deposited here. So this is called the vapor transport. So all these three mechanisms, surface diffusions, lattice diffusion, and vapor transport, they will cause material movement from the concave surface, from the convex surface to the concave surface. But unfortunately, all these three mechanisms, 1, 2, and 3, they are called non-densifying mechanisms, because they don't cause any eliminations of the porosities. They are only, what they entail is that the material is only moving from here to here, but then there is no removal of the porosities. Because there are no removal of the porosities, these three mechanisms, that is the surface diffusion, lattice diffusion from surface, and vapor transport, they are called non-densifying mechanisms. So what they actually do is they are only coarsening the particle. So they help in coarsening the particle. So they are causing this. They are causing this coarsening. The surface diffusion, lattice diffusion from the surface, and evaporation condensation, that is the vapor transport, only cause the coarsening of the material. So they are non-densifying mechanisms, and basically they are bad. They will lead to coarsening, not densifications. So then what will cause the densification? So densification will cause by the grain boundary diffusions or lattice diffusions from the grain boundary. And how does that happen? So if you think about it, here there is a concave surface. Under concave surface, the vacancy concentration is higher. So the vacancies will move from this concave surface to the grain boundary. And grain boundary can do a magic thing. What they can do is they can eliminate the porosities. They can generate the vacancies, or they can eliminate the vacancies. So these vacancies under the convex surface, they move to the grain boundary and they get annihilated at the grain boundary. And because the grain boundary can annihilate the vacancies, so they are effectively removing the pores. And that is why grain boundary, when the grain boundary diffusion and lattice diffusion from grain boundary, anything involving grain boundary, has the potential to eliminate the porosities by annihilating the vacancies. And that is why these mechanisms are called densifying mechanisms. Okay. So surface diffusion, lattice diffusion, and lattice diffusion from surface and vapor transport, they are the non-densifying mechanisms. And grain boundary diffusions and lattice diffusion from grain boundary, these two are the densifying mechanisms. So these two mechanisms, if we can somehow activate during the sintering process, then we'll end up with a dense product. Now the question is, how can we avoid the surface diffusion and we can increase the grain boundary diffusions? So how to do that? So fortunately for us, there are ways to do that. For example, So surface diffusion is generally the worst thing that we want to avoid during the sintering process. And also surface diffusion have the lowest activation energy, whereas the lattice diffusion and grain boundary diffusion has higher activation energies. Because of that fact that surface diffusion have the lowest activation energy, generally surface diffusion dominate over the lattice diffusion and grain boundary diffusion at the lower temperature. So surface diffusion is generally faster at lower temperature, whereas grain boundary diffusions and lattice diffusions, which can help us to densify the material, dominate over surface diffusion at the higher temperature. So that is also another reason why we need higher temperature for the sintering process. Why we need higher temperature? So higher temperature, you might ask, what do you mean by higher temperature? So generally higher temperature means it is higher than the 0.5 melting point. So you can imagine that surface diffusion will be faster at less than 0.5 melting point. So these we call it as a lower temperature, and higher temperature means higher than 0.5 melting point, where the grain boundary diffusion will actually dominate over the surface diffusion and we will end up with a dense product. So this is about the mechanisms of sintering process. So sintering process, just to conclude couple more things. So Koebel has divided the whole sintering process into 3 stages. The first is the initial stage where the particles come close together and touch to form this neck, right? The small connections between the particles, which is called a neck. So this is called the initial stage where the neck forms. And the second stage is where the particles then continue to densify and still have a continuous network of pores. That is called the intermediate stage. So initial stage, the particles have, the body has theoretical density of around 0.5, density of 0.5, theoretical density around 0.5 to 0.6. In the second stage or in the intermediate stage, the material will have a density of, let's say, 0.6 to 0.9 theoretical density. And the final stage is where there are no continuous channel of pores, but only isolated pores remaining. That is called the final stage. And in the final stage, generally the density will be around 0.9, greater than 0.9 theoretical density. So based on that, the sintering processes has been subdivided into 3 stages. Okay, so so this is about our introduction to sintering process. Okay, so now let me talk about the types of sintering. So sintering has been also subdivided into 2 different types. One is liquid phase sintering. So liquid phase sintering is where during the sintering process there is a evolution of a liquid phase, then it is called a liquid phase sintering. But if during sintering process no evolution of liquid phase happens, then it is called solid state sintering. So sintering is again subdivided into 2 different parts. Okay, so with that, we are more or less done with the introduction to little bit of ceramic processing and the sintering. Now I will go into talk about the flash sintering process. Okay, so flash sintering is a part of field assisted sintering technique. So field assisted sintering technique is different from conventional sintering, which I have discussed till now. So in conventional sintering, you take the pressed green product and put it into the furnace and you are done. So that is traditional ceramics, but traditional sintering. But in case of field assisted sintering, what we do is we put the sample inside the furnace, and not only we introduce temperature, but also we pass some amount of current or apply an electric field in addition to the temperature. So when we do that, we call it as a field assisted sintering technique or FAST. So here is the one example of that. So here is a product, the product which we want to densify. This product is put inside a graphite die, and this graphite die, there is a plunger through which we apply pressure, and also we pass DC current, DC pulsed current, very high amount of current. It is around 10 kiloampere. So that much high current we pass through the sample. So due to this current, there will be resistive heating, which will increase the temperature, and also some amount of current can flow through the sample. So due to the effect of combinations of electric current, electric field, and temperature, the material densifies much faster compared to the traditional ceramics, like within a couple of minutes compared to hours. And these techniques are called fast. So many of you may have heard of the spark plasma sintering, or SPS. So SPS is not any different from field assisted sintering technique. But nowadays, we generally don't like to use the term spark plasma sintering because um, the spark plasma sintering was invented in 1970s, and those days people thought that material densify um, during the spark plasma sintering due to formation of spark and formation of plasma. But latest research has shown that during SPS there are very scant evidence of spark and almost no evidence of formations of plasma. So the spark plasma has become a misnomer because there are no spark and there is no plasma. So nowadays we like to use the term as field assisted sintering technique, or FAST. So now, now come to flash sintering. So flash sintering is a new development in field assisted sintering technique, or which was traditionally known as SPS. So it's a subset of this field assisted sintering technique, but it is also unique compared to, or different from, the SPS technique, because in the flash sintering, we apply much higher electric field and we pass through much lower current compared to the fast or the SPS technique. And because of that, we don't apply that much of current and so on. So it's basically an inexpensive setup. And more than that, actually, in flash sintering, what has been observed is that the material densify in few seconds rather than few minutes. So it is even much faster compared to the SPS or the fast. And that is what we are excited about in case of flash sintering. So if we think about flash sintering, so flash sintering is part of the field assisted sintering technique. That means we apply a current and electric field in addition to temperature to densify the material. So that is why flash sintering is a part of field assisted sintering technique. And if you think about the flash sintering, so flash sintering is a relatively very new invention. So flash sintering was discovered by Professor Rishi Raj at University of Colorado Boulder, US in 2010. So it was discovered at Rishi Raj's group, Professor Rishi Raj's group in 2010. So it's much newer invention compared to spark plasma sintering, which was invented in, I think, 1950s and 60s. So it's much relatively new invention in case of sintering and ceramic processing. And we ceramic scientists, we are very much excited about flash sintering for many different reasons. So one is shown here. So if you think about zirconia, ZrO2, it's a very common ceramic material used for many different applications. One such applications most of you will be familiar with is a dental crown. So dental crowns, they are traditionally made from zirconia. So, so this zirconia, if you want to sinter zirconia, traditionally it requires 1400 degrees centigrade and few hours, like 3 to 4 hours, to densify zirconia. But what Professor Rishi Raj has shown at Colorado Boulder is that through flash sintering, it is possible to densify zirconia at 850 degrees centigrade furnace temperature, so much lower furnace temperature, like 500 degrees centigrade less furnace temperature, which is huge, and also in few seconds rather than few hours. So it's much faster and requires much lower temperature compared to conventional sintering. So it's really a game changer, or it can be a real game changer in case of ceramic processing because of that such advantages. And nowadays, if you think about it, the biggest problem that we are facing is the climate change, greenhouse gas emissions. And so all the government around the world, they are trying to reduce the energy consumption through different ways. And ceramic industry is actually very energy intensive. And one of the reason it is very energy intensive is because the ceramic, as I mentioned, product requires sintering, and sintering requires very high temperature. So ceramic industry is very energy intensive. So if we can develop these new techniques like flash sintering, it will be huge beneficial for the society at large. So that's why we are really very excited about this flash sintering technique. So what are the features of flash sintering? Ultra fast densifications, as I mentioned, in few seconds compared to few hours in traditional ceramics, at much lower furnace temperature, 850 compared to 1400 degrees centigrade. And flash sintering also occurs with a bright light emissions followed by a power surge. And this bright light emission is why it has been named as flash sintering. So it occurs with a flash of light. So that is why it has been named as flash sintering. And flash sintering also accompanies a sudden electrical resistance drop. Okay, so I think we have so features I have just mentioned. Now, if we think about the mechanisms of flash sintering, unfortunately, it's not very clear till now why flash sintering, during flash sintering, the densification happens so much faster compared to traditional sintering, and also at much lower furnace temperature. So there are a few proposed mechanisms. One of the proposed mechanism is thermal runaway by joule heating. So what they propose is that I think, yeah. So this is a video. I don't know if it will be playing or not. Okay. So video is not working, unfortunately, I think. Okay. So, but this is actually the what happens during flash sintering. So if you have a dog bone samples, and here are the platinum wires through which you pass current, and current passes through the material. So what happens in the theory of the thermal runaway is that as the current passes through the material, due to joule heating, the temperature of the sample increases due to joule heating. And in the ceramic materials, especially oxide ceramics, it has been observed as you increase the temperature, the conductivity increases. So conductivity increases with the increasing temperature. So you pass current, joule heating, increased temperature, increased conductivity. Increased conductivity means even more current passes through the sample. So even more current passes through means even more joule heating, even more increased temperature. So increased temperature means even more conductivity. So there is a positive feedback loop. That positive feedback loop of joule heating and increased conductivity leads to pretty high temperature, and this um, feedback loop will cause a thermal runaway, and that people have proposed as one of the mechanisms to explain the such a high such a ultra fast densifications during the flash sintering. But of course that is not all, because there are still debates, like there are other mechanisms which are also possible, like defect nucleations and electrochemical reactions. If we have time, then I think maybe I will little bit explain this mechanisms as well. And the flash sintering has been also subdivided into 3 stages. Stage 1 is where the material is resistive and the power source is under voltage control and the heating rate increases. And in the second stage, the peak power achieved, the power goes to a maxima, and the power supply changes from voltage control to current control, and the heating rate is very high. And then there is a stage 3 where the power supply is under current control, and there is a the temperature and the power stabilizes in the material. And these are the flash sintering apparatus people have used. So this is originally used by Risiraj. So this flash sintering, they have used a dog bone sample, just I've shown you. and these are platinum wires through which the sample is hung inside a furnace. So this is a tube furnace, in fact. So you increase the temperature to certain, like 850 degrees centigrade, and then you pass current through the material and the material densifies. And they also have a thermal camera to monitor the sample shrinkage simultaneously with the flash sintering. And people have used a different setup also. These are some example of different setup that people have used. And in the next few slides, I'll also show our own setup that we use at IIT Patna. And people have used different sample geometries also. One of the original one was the dog bone sample, which is used by Rishiraj, but later people have tried with bar-shaped sample. They have tried with cylindrical samples as well. So different cylindrical samples with different aspect ratios also people have successfully used for flash sintering. Okay, so so I have talked about the thermal effect of flash sintering, but so in flash sintering there are also some additional thing people have observed. For example, there we have in 8 mole percent yttria stabilized zirconia, there is a evidence of ion migrations. In Syria during flash sintering, people have seen asymmetric lattice expansion. In titania during flash sintering, they have observed texturing induced by electric field. In 3YZ, people have shown nucleations of metastable phases. So these phases disappear when we stop passing current to the sample. But once again, if we start passing through the sample, there is a nucleations of a metastable phase that people have identified during flash sintering. And in zinc oxide, people have observed abnormal grain growth in the anode side. So these all indicates that flash sintering is quite a complicated phenomenon. There is not only Joule eating thermal runaway, but also there are additional effects which cannot be explained through Joule eating and thermal runaway. So we also have to consider the other two mechanisms which people have proposed. Okay, so this is the Rishiraj's own experiment of flash sintering, the initial experiment that he has conducted in his lab. So if you see that, so in his case, he has done the constant heating rate experiment. So he increased the temperature of the furnace at a constant rate, for example, like 10 degrees centigrade per minute. And he has kept the sample at this particular voltages, like initially without no electric field, so 0 volt per centimeter, no electric field. And you see that the material starts to densify at around 1200 degrees centigrade, and only partially densifies even after reaching around 1450 degrees centigrade. But when he applied electric field, small electric field of 20 volt per centimeter, we see that materials start to densify at 1100 degrees centigrade, so slightly lower temperature, and it densifies much better compared to without electric field. And then he slowly increased the amount of electric field, 40 volts. Again, the materials start to densify earlier and densify to greater extent. This is the linear shrinkage, by the way. But it's okay. It's not something out of ordinary. But when we increase the electric volt to even higher level, like 60 volt per centimeter, what is observed is that the densification is done in like few seconds. It's almost like horizontal line. So very fast and ultra fast, basically densifications that happens during flash sintering. And that is what is the flash sintering is all about. It's so fast. And also you see it happens at much lower temperature, just as I mentioned just before. Okay, so this is about like an introduction to flash sintering. To summarize that, flash sintering is a field stress sintering technique where we apply an electric field with addition to in addition to furnace temperature. And during flash sintering, there is a very fast, ultra fast densification. Material densifies within a few seconds and at much lower temperature compared to the traditional sintering techniques. And also flash sintering, people have been successfully done. Initially, he has done it in 3YZ, 3 mole percent yttria stabilized zirconia. But later he has confirmed that in 8 mole percent yttria stabilized zirconia. Then many people have done successful flash sintering to many different ceramics. For example, titania, Syria, then aluminum, and many other different ceramic materials has been successfully flash sintered. Okay, so that is all well and good. Flash sintering is like very less energy intensive. It's and so on. So it has a lot of potential, but there are also problems with flash sintering. So what are the problems? So problem is that what people have observed is inhomogeneous densifications. Inhomogeneous densifications that comes about due to many different reasons. I'm not going to go into too much detail because already I see that it's more than 1 hour over. But that has been observed that the material doesn't densify homogeneously. There has been inhomogeneous densifications that people have observed, which is bad. Of course, we want to avoid that. And due to inhomogeneous densification, we have also seen crack development and cracking of the samples during the flash sintering, which is again very bad. People have observed microstructural heterogeneity. For example, the grain sizes are different in the anode region, different in the cathode region, and also different in the core of the sample. So there is a gradient in the grain size that people have observed from the anode section to the cathode sections. So anode is the positive side of the electrode and cathode is the negative side of the electrode. And also people have observed electrochemical reactions, that is the blackening, which you can see here, some amount of blackening which has started here and propagated from here to here. So this electrochemical blackening is also something people have observed during flash sintering. So these are all like currently the issues that we encounter with flash sintering. So till now, only small samples, laboratory scale sample has been flash sintered successfully. Larger samples, it's difficult to sinter with flash because of the inhomogeneous densifications problem. People are trying to solve that, and at IIT Patna, we are also trying to solve these issues related to flash sintering. So if we come to our own results, which I will briefly mention in next 15 minutes or so, is we are trying to solve this inhomogeneous densification problems with different strategies we are trying. One of the strategy that we are trying is using dopants. So in this work, we have added dopant, that is ZNO, into 3 mole percent ATR stabilized zirconia to see if we can solve the inhomogeneous densifications and cracking problem in the 3Y set that people have observed. So this is our work. So we have taken, so if we, okay, so let me little bit talk about our own setup. So this is actually our own setup that we have made at IIT Patna. So our setup is slightly different from what Professor Risiraj has done, but this is similar to work done by other scientists. So in our setup, this is our furnace. And inside the furnace, we have furnace furnitures, for example, alumina discs. So these are our alumina discs. And these alumina discs have holes through which we have put these alumina rods. And the purpose of that is that these discs can move freely up and down during the flash sintering process. And in between the alumina discs, we put our sample. And between our sample and the alumina disc, these are our electrodes. These electrodes are connected to our DC power supply, which of course remains outside of the furnace. And through this wire, we pass current, and then current through electrodes pass through our samples for the flash sintering. And our furnace also have a quartz window through which we have put a camera. We can capture the image of the sample during flash sintering. From that image, using digital image correlations, we can calculate the shrinkage of the sample. And simultaneously, we also record the voltage, current, and power that is being supplied by our DC power supply. And we have written our own MATLAB code for doing this. So simultaneously, we record the shrinkage data and also the voltage, current, and power data from the flash sintering experiments. And this is our sample geometry. So we have used cylindrical samples with 6 mm dia and 6 mm height. And these are the process parameters we vary. I will not go into that. So let's little bit talk about our experimental parameters. So we have taken 3 YZ powders, so nano-sized powder. So again, in flash sintering, people have observed that it only works with nano-sized particles. So we have also gone for that. So these are 700 nanometer particle size, basically. 3 YZ we purchased from Sigma Aldrich. And dopant, we have used zinc oxide as mentioned earlier. And these are again from Sigma Aldrich. So we have mixed this powder, 3YZ powder and ZNO powder with required amount. We have varied that from 0 to 8 mole percent and mix those powder in our ball mill to get an intimate mixture. These mixtures are then pressed in our hand press to make the pellets like 6 mm dia, 6 mm height. And the grain density we get after pressing is around 50%, which I mentioned that generally that is the case for most ceramics. By by pressing at room temperature, you are not going to get much densifications. So we get only 52% relative density. And these pellets are put into our flash sintering furnace, which I've just shown earlier. And we have done the flash sintering at different current, voltage, temperature, and so on. And after that, we have done measured the density. We have done the phase analysis through X-ray diffractions, microstructure analysis through FESCM, and DIC for measuring the shrinkage. And this is our flash sintering experiments. So you can see our flash sintering setup. This is our alumina discs. These are alumina rods. These are the electrodes, anode and cathode. In between, this is our sample. And we also wrap around the sample with a glass wool to prevent thermal shock on the sample surface and prevent cracking. So this is the image before flash sintering. This is the image during flash sintering. You can see that during flash sintering, the sample becomes incandescent and it emits a lot of light, so it glows. And this glow you can see through the ceramic wool that we have wrapped around the sample. And this is after flash sintering, the sample cools off. But one thing you can observe here, which we have observed, that anode always remains hotter than the cathode. And currently we do not know why exactly that is the case. So this is our flash sintering experiments that we have done. And this is the sample of before and after flash sintering. So this is our initial samples. This is 6 mm length. And we can see that after flash sintering, the sample shrinks. And so you can see that the height has reduced. So for 3YZ without any doping, we have seen that a lot of cracking in the samples. So we can see here cracks at the middle of the samples. So this is an image of the cracks that we have collected. So for 3YZ, it's difficult to make a crack-free product to flash sintering. But what we have observed is that if we add little bit of ZNO dopant, we see that no, there are no cracking, the sample remains intact. And one more thing we observed is that if we add the dopant, we see the more amount of blackening on the sample surface, the electrochemical blackening. So 2Z, there is very little, but in 4Z, that means 4 mole percent ZNO additions, we see more amount of blackening of the samples. And with 8Z, we can see that the blackening has almost covered the sample surface. So this is also something we have observed, that during flash sintering, when we added the dopants, there is more amount of electrochemical reactions, which leads to electrochemical blackening. So these are our electrical parameters that we have collected, recorded during the flash sintering experiments. So this is voltage. So this is stage 1. We slowly ramp up the voltage, that is the field, into the sample. And here we see the flash event. So during the flash event, you see the current remains almost flatline and then suddenly it starts to increase. And this increase entails the flash event, where suddenly the conductivity of the sample increases very rapidly. So this is the flash event. And after the flash event, again, the power supply, we change from voltage control to current control, and we have to do it, otherwise the power will increase and that will burn the samplet completely. So we limit the power supply and change that to current control mode so that it remains flatlined. And simultaneously, we see that there is a power spike. So power increases and then saturates. So this is stage 1, this is stage 2, and after that we have stage 3, which is shown here in the right hand image. And simultaneously with the power spike, we also see the sample shrinkage, which indicates the sample gets densified. Now, so this as a relative density. So relative density with 3YZ without ZNO dopant, we observe that around 85-86% relative density. So with ZNO dopant, we see small improvement. We get around 90% relative density. With more ZNO dopant additions, we don't see any further improvement. So relative density maximum we have got till now is around 90% relative density through flash sintering in case of YSZ. And these are corresponding the shrinkage curve and shrinkage rate that we have calculated. And this is again for different mole percent ZNO additions. We have also calculated the we have also recorded the power density curves, and from this power density curve actually we can predict the sample temperature by doing a simple calculations, and from that we have also plotted the conductivity versus 1/T plot, and the slope of the curve gives the activation energy for the ionic conductivity. And actually this matches very well with the literature data that is recorded for 3YZ samples, but with ZNO additions we see also evidence of changing in the slope. So this is something we are now actively investigating actually what is going on during the flash experiment. But what we can conclude is that generally during the flash event we don't see much change in the conductivity mechanisms, at least for the 3YZ samples. And this is the microstructure. We see that the grain sizes different increases as we increase the amount of ZNO dopant. It increases quite significantly from 400 to 1800 degrees centigrade. And also we see that in the anode and cathode there is a difference in the grain size. Okay, so these are again, I'll not go into the detail because we are running out of time. So, so we have also done X-ray diffraction studies, which confirms that ZNO do get into the 3YZ lattice, and we see the peak shift using X-ray diffractions, which confirms that. We have also done the Raman study. Here we get something interesting because we have done the Raman on the darkened phase, and which happens due to electrochemical blackening, and also the white phase. And the black region actually, if we compare, this shows a defective T double prime tetragonal phase, whereas the white region shows a tetragonal T phase. So this is kind of an interesting, which we are investigating currently right now. In the Raman also, in the white phase, we see a peak shift, which indicates that what our X-ray says, that ZN do go into the 3YZ lattice. And this is again the electrochemical reactions. Again, I don't think I will have time to go into that. So, so the electrochemical reaction basically happens because 3YZ or zirconia is an ionic conductor, so it cannot directly conduct the electrons. So the charge carrier is actually the vacancy of oxygen. So oxygen vacancy is the charge carrier in the ionic conductor of zirconia. And so there are electrochemical reactions. This reaction 1 happens at the anode and cathode. The reverse reactions happens at the forward, and the reverse reaction happens at the anode and cathode. And if so what happens is that oxygen vacancy generates here at the anode, and it gets annihilated at the cathode by absorption of the electrons. If both the reaction happens at the same rate, we don't see any electrochemical blackening. But when this reaction is obstructed because oxygen cannot come into the lattice because of the blocking of the anode, we see electrochemical reactions. And we also observe that if we create more oxygen vacancies by doping, which we have confirmed through our ZNO doping, we see that electrochemical reactions increases. Okay, so so this is about our own experiment. So I have actually come at the end of this presentations. So let me conclude about our own experimental results here. So ZNO is likely acting as a sintering aid, and we see that small amount of ZNO additions is actually improving the densifications from 85 to 90%. But more amount of ZNO if you add, that doesn't improve the densifications any further. But also we observed that ZNO doping somehow decreases the cracking in the sample, and we currently don't know exactly why that happens, but this is something we have observed. And we have also seen that there are non-thermal effects on the microstructure. With more amount of ZNO doping, we have seen that increase in the grain size, which we believe is due to the more amount of oxygen vacancy leads to higher diffusions, which leads to the increase in the grain size. And finally, we have also observed that ZNO doping promotes reduction of 3YZ into non-stoichiometric zirconia, and we have confirmed the phase is a T double prime defective tetragonal phase, which forms due to electrochemical reactions during flash sintering. And with that, I will conclude today's talk. So I must thank everybody for listening, and I'll be happy to take questions from the audience. Thank you.
Yeah, dear participants, if you have any questions, you can pose. Dr. Chakravarti is there to take your questions, or you can post it in the chat box. I will let him know what are all the questions.
Yeah.
I experienced one peculiar problem, Professor.
Yeah.
We were
Please.
working on aluminum CNT composites long back, around 4-5 years back, and we used to do sintering. But after sintering, when we take out the sample used to get crumbled. So what might be the reason? After a lot of, might be around 1 year of work, we could not arrive. Then we changed the process of densification, the compaction process we changed. Then little bit we were able to achieve. Then again, we were not satisfied with the results. Again, we went for the die design. We changed the die design, and during the sintering process, we went for a different route. Then we were able to achieve a little bit. But if we compact it, and as such, if we keep the sample in the sintering furnace, after sintering, if we take out, it used to get crushed. What might be the reason?
One problem is, so this is aluminium, right?
606 series alloy, along with the CNT.
And
Carbon
powders you have used, right? Powders.
Yeah, powder. It's powder metallurgy road. We used to ball mill it for around 2 hours along with CNT. The CNT used to be coated with a material to have good interface. Then the green compact was there made, and the green compact was sintered in a furnace.
And at pretty high temperature, right? The melting point is 600. So
we used to do it. We tried at different temperatures, right from 450 to 600. We tried,
but it doesn't help
and
much.
we could achieve a little bit of yes, sir.
So what I suspect, maybe it is possible that the particles are getting oxidized. Maybe they are getting some thin layer of oxide layer on the surface, and maybe that is preventing densifications. I mean, that is my speculations. I don't know for sure, but
yeah, probably we also thought that probably it is getting oxidized in the process. Then we started using argon to create an atmosphere, so that inert atmosphere. Then little bit we were able to achieve. Is there any? Because I wanted to try spark plasma sintering also. During that time, the machine was out of order. I could not try. I wanted to try with microwave.
So spark plasma might help. Might help. I think.
But the size
also
is
because there also you also apply pressure, so that also helps. Creating the particle contact. Then the free sintering, like without.
I wanted to try microwave sintering. How about microwave sintering? Is it helpful for those kind of things?
I don't think microwave will work with metal. I'm no expert, but I think generally it doesn't work with metals. I think because I think
Basically
metal
for
doesn't
ceramics.
allow doesn't allow this microwave to penetrate. So maybe you have
but
to
I used to work on nickel titanium alloys long back. I used to use a vacuum induction furnace. And we used to change the power factors and we used to do melting of nickel titanium.
Yeah, so I think
In
induction
that
might
case,
work.
probably induction furnace also we will melt non-ferrous furnace, no? Any modifications can be made
Mm-hmm.
and can be made. That's just a academic interest.
I think it can be made. You can make it, I think. Change it for
Uh,
sintering rather than
okay,
melting,
I
right?
brought a home furnace and tried to do some modification with you.
Mhm.
Possible.
I think can be done. Maybe possible, I think. Maybe
Okay.
possible.
It was very informative.
Should
Yes,
I
yes,
ask a
sir, yes,
question?
sir, please, sir.
Yeah.
Myself, Dr. Pankaj Kumar Singh from ITBHU.
Yes.
Your presentation was nice regarding the sintering process.
Mhm.
What is difference in the type of furnace used for liquid and viscous sintering process? Can you explain that thing?
The difference in the furnace
Yes.
for liquid phase sintering and viscous sintering.
Yeah.
Um, Furnace, I think you can do it in any furnace in theory. I think there should not be any problem for liquid phase sintering. Only it can be an issue if you use something like vacuum, which might accelerate some evaporations of phases. Other than that, I don't see much problem in the furnace itself. Because we do traditionally, most ceramics are actually made by liquid phase sintering only, and they use the normal furnace like electric furnace and so on. And there is as such no such issues.
Okay. Thank you.
Okay.
Any other questions, my dear friends, my dear participants? So you are getting messages like session is highly informative.
Oh, that's great.
Okay, sir. I think it's a new technology. What you are telling, we were having little bit knowledge of spark plug sintering. Now we have exposure to
Mhm.
flash sintering. I think the pretty concept is both are almost same, no?
Yes, it's pretty similar actually.
It's
It's
similar. So yeah, probably it will give good result probably in near future for this
yes.
kind of work. Okay, thank you
Mhm.
very much, sir Chakravarti sir, for giving such a
Okay.
highly informative and recent technology for our dear participants. On behalf of our management and the college, Dr. Ambedkar Institute of Technology and Department of Mechanical Engineering, we wholeheartedly thank you for giving such a good lecture in this faculty development program. Faculty development program. Thank you very much, sir.
Okay. So thank you very much for giving me this opportunity also. Okay.
Okay, sir. Thank you. We are highly honored to
Okay.
have with us.
Okay.
Dear
So
participants, uh, the session link, that is a feedback link, will be is shared. Yeah, you can give your feedback on the session. Afternoon, we will join, and probably I have requested Pankaj Kumar Singh because he has also got good knowledge about. He's working on bio. I am also very eager to listen at least half an hour from him. Then I will just give you a brief overview of what I have done little bit so that we'll conclude. Again, that is an extra session what we are taking today afternoon. We will have half an hour or 1 hour of session, and then we will move on to the that is your test quiz, and then we'll do valedictory so that you can give your results after once the results questions are posed. Then we'll start evaluating and give you the results. Pankaj sir, is it okay, sir?
Yes. No, sir. But whether I have to give the presentation, sir?
If you have presentation, you can give, or if you want to do extemper also, you can do extemper.
Okay. Okay. Thank you.
As your wish, half an hour. Just I wanted to become curious that since your questions are so good,
But I am interested to listen you, sir. You are the
I will
convener
also
and
give, sir.
you.
I, I will also give. Not a issue. I will also give, sir. We'll also listen because we will know what work you have also done because you're talking about bio.
Yeah. Thank you.
Exports certainly will use of near future.
Okay, sir. Okay. Thank
Is it
you.
okay, sir? Okay, sir. Okay. Thank you. Then we'll leave this meeting here, and again we'll join exactly at 2:30 in the afternoon.
Hello.
Hello, good afternoon, participants. The last session of the FDP is going to start in another 2 minutes. Dr. Pankaj Kumar Singh, sir.
Yes, sir.
Yeah, are you ready, sir?
Yes, sir.
Yeah, can you share the screen, sir,
Okay, sir.
of your PPT so that I can check? Yeah, make it full screen, sir. Yeah.
Okay.
Can you move the slide, sir? Second slide. Yeah, it's moving, sir. It's working. Sir, you can start the Pankaj Kumar, sir.
Yes, sir.
Is it audible?
Okay.
Yeah. You can start, sir. All the participants are there. You can start your session, sir.
Okay. Thanks a lot.
Yeah.
Thanks a lot, Dr. Raju, sir. You have
Just a
allowed
minute, sir.
me.
Just a minute.
Yes.
1 second. Raju, sir, want to speak something.
Yeah, good afternoon, dear participants. Today I have the privilege of inviting. See, it's a what we tell. It's kind of a quiz what we used to get at IITs, right? Like that. Today I have requested Dr. Pankaj Kumar Singh to present his work so that we can also listen, because he was very active throughout the FDP program, and I learned that he has done very good work in biomaterials. Hence, I requested him to present few work what he has done. So, in this connection, he has readily accepted. He has just taken 1 hour to prepare, and he is presenting his work. Later on, I will share my view of what work I have done. It will not take too long, because this session we have to complete even the test. So after he does, I will take about half an hour, 1 hour, and we'll finish off the session. I welcome Dr. Pankaj Kumar Singh to this afternoon session. Pankaj Kumar, sir, welcome you, sir.
Yes. Okay. Thank you, sir. Am I audible, sir?
Yes, sir, you're audible, sir. You're audible, and your PPT is also visible clearly. Over to you, sir.
Okay. Thank you, sir. Myself, Dr.
You can
Pankaj
show
Kumar.
your face, sir. We can see you, because later on it will be good so that we can see your face.
Actually, sir, there is problem in my camera, sir. Maybe in the
Okay.
discussion part, I will open the camera. There is some
Okay.
problem in.
Okay, sir.
Then excuse, sir, for that.
No problem, sir. No problem, sir. Thank you, sir. You can continue, sir.
Thanks a lot. Myself, Dr. Pankaj Kumar Singh from IIT BHU, and today I am going to present some important points regarding this FDP and the nanotechnology, and whatever the things that is related to the nanotechnology. I am going to present that thing. First of all, if we start the nanotechnology, nanotechnology is basically the study on the nanomaterials in the range of 1 to 100 nanometers that we already know. Here we use the microorganisms. In the biological study, we use the microorganisms, and in the microorganisms, we are considering the 3 kingdoms of the Vitaker-5 kingdom. That is the Monera, bacteria and cyanobacteria, Protista, that is the microalgae and the protozoa, and the fungi, molds and yeast. These are used in our the biological study. Then here one terminology came the plasma versus the blood plasma. We are generally studying on the plasma, and here how it is related, I want to show. We have to know this, that the plasma is the 4th states of matter, and the blood plasma is the liquid portion of blood, and it consists of the free electrons or ions that aren't bound to an atomic nucleus. For example, there is the lightning, the aurora, and the solar wind, the tail of a comet, star, the earth ionosphere, a welding arc. These are the examples of the plasma. We should know the difference between the two. Next, there is coming the MATLAB. it is also working in the same principle related to the mathematics, that the matrix laboratory. Here the easiest mathematics program language and produces the 2D and the 3D images. This is the, and the important thing here is the letter and digit. Between these there should be an underscore. This is the important point. And the logical operator symbol, this is represents the not. And the row separated by the comma and the column separated by the semicolon. There is another terminology in the MATLAB, that the Simulink. Simulink is a MATLAB-based graphical programming environment for modeling, simulating, and analyzing multi-domain dynamic systems. Here, this I am present this MATLAB as it is also going to the nanotechnology study also. Next is the semiconductor. It is very important part in the research, mainly the ceramic or in the bio also. This type of work in the material science also are doing. Here we know the semiconductor. Semiconductor is the resistance is between the metal conductor and the insulator. This is the quality of the semiconductor, and types are mainly the two types: the intrinsic, that's the pure, and the extrinsic, that's the P and N type. And next, there is the silicon and germanium are called as the intrinsic. And semiconductors are applied in the integrated circuits, diodes, and transistors. This is also a very important part of the nanotechnology. Next, in the biological process, how we synthesize the nanoparticle, that I'm going to explain here. When the synthesizing the silver, gold, bimetallic, that is the gold silver nanoparticles from the mold strain, that I have already mentioned before. There is in the biological process. Here, what we take, the 100 ml of JPEG of froth media is prepared. After then, we go on to inoculation of mold into the medium, and then we incubate at a specific temperature for a specific time. After then, after incubation, there is a separate cell biomass by filtration and wash thrice with distilled water. This is done, maybe by the centrifugation also. Wet biomass suspended into an Erlenmeyer containing 100 ml of each silver nitrate, gold chloride solution, or both. And after then the culture was incubated. This is the basic process. As I am having very less time, so I have to go on very fast. So I am just showing this thing, and basically what process I want to explain that thing. There is an incubator that we should know. These instruments are very important for the biological study. And second, that the centrifugation process. There's the laminar airflow, LAF, we use for our study. And after then, we have to maintain proper microorganism arrangement, so that there must be not be any contamination will occur in such type of study. Next, another very important part of the nanomaterial is the quantum confinement. In the quantum confinement, we know that there is different types of the nanomaterials, their properties, and there's the degree of confinement, and there's the degree of freedom. And after that, there are some examples. Here we are generally going to very confused about the dimension. Actually, dimension is not based on the degree of confinement, but that is based on the degree of freedom. That we should know, that whenever we are saying that the zero dimension means that is the degree of freedom is 0. And similarly, what is this? That all dimensions are at nanoscale. Nanoscale that I have already explained, the 1 to 100 nanometers that is considered. And this the degree of confinement will be 2 dimension. And examples are quantum dots, the nanodots, and the fullerenes. These are the examples. Next, there are the types of nanomaterials, the 1 dimension. 1 dimension we consider, that is the degree of freedom is 1 dimension, but the degree of confinement is 2 dimensions. Here I have already mentioned, you can read that the 2 dimensions at nanoscale and 1 dimension outside of the nanoscale. And in the example, you can consider the nanorods, nanotubes, nanowire, quantum wire, nanofillers, carbon nanotubes. These are coming in the 1 dimension. Next, there is the 2 dimension. What is the 2 dimension? Again, it is the degree of freedom, the 2 dimension. And next, there is the degree of confinement, that is the one dimension. And in terminology, it is a one dimension at nanoscale and two dimension outside of the nanoscale. And in the example, we can take the graphene nanosheet, nanofilm, quantum wells, nanolayers, nanocoatings, and thin film. These are the in the two dimensions. And next, there is the three dimension. In the three dimension, again, we consider the degree of freedom, that is the three dimension, and the degree of confinement, that is the zero dimension. And here, no dimension at nanoscale, that is, all dimensions are beyond the nanoscale. And in example, the three dimension, there's the bulk powder, the cauliflower, the bundles of nanowires, diamond, graphite, dispersion of nanoparticles. One very important formula, that is the when we add the degree of confinement and the degree of freedom, that is dc plus df, it should be equal to 3. This is the formula we should consider. Next, we go on to quantum confinement and the quantum number. Is the confusing terminology, and in the earlier time, that is the intermediate class, we study about the quantum number. Then I have thought that there is some confusion and this should be cleared in this stage also, in the research stage. So I have gone to explain the difference between this quantum confinement and the quantum number. The quantum confinement, what I have already shown, that control on the freedom of electron hole, that exciton, is one or more dimensions. It gives rise to 0 dimension, 1 dimension, 2 dimension, and 3 dimension. Next, the size equivalent to wavelength of electron. And at last, there's the high discrete energy, the discontinued energy. These are the properties of the quantum confinement. And we all know that the quantum number that we have already studied from the intermediate and high school also, we have studied some part of that. And in the BSc and MSc or in the BTech also, we are reading on this, the quantum number. This is the basic thing. It is used to completely describe all the attributes of the given electron belonging to a matter. As we know, there are the 4 quantum numbers, basically the principal quantum number, the orbital quantum number, orbital angular momentum quantum number, you can say, or azimuthal quantum number. And third, that is the magnetic quantum number that we know. And fourth, that is the electron spin quantum number. Okay, what is the difference in the 4 quantum number that we already know, but we are going to confuse also during those times. So we should revise that thing also. What is the principal quantum number? If we know that it is represented by the n, and it represents the number of shell. Example, that is 1, 2, 3, and so on. And second, that the orbital angular momentum quantum number or azimuthal quantum number, that is denoted by L, and it represents the number of subshells. If we consider the principal quantum number, there is the orbital angular momentum quantum number, there is the 0, that the S, and 1, that the P, 2, that is the D, and 3, that is the F, and so on, that is the N minus 1. And the third, that is the magnetic quantum number, that is denoted by the M. It represents the number and orientation of the orbitals in the subshell. Example, you can take the -1 to +1, that's the -1, 0, and 1, and so on. You can take that point. And the fourth and the last one, that is the electron spin quantum number, it is denoted by F. Example, you can take the +1/2 and -1/2. These are the basic things about the quantum confinement and the quantum number. Next, as we are doing some research work, which are the funding agency of the government of India, we should know. That is the first, the All India Council for the Technical Education, AICTE, that is organizing this program also. So we should know that thing. Next, the CSIR, there's the Council of Scientific and the Industrial Research. Next, the DRDO, Defense Research and Development Organization. It is also doing on the corona also. We have heard about the they have given the fund for the research on the corona, and some medicine also has been discovered by this department. And next is the Department of Atomic Energy. Next is Ayush. We already know this is also funding to the research. There's the Department of Ayurveda, Yoga and Naturopathy, Unani, Siddha and Homeopathy. And next is the Department of Biotechnology, the DBT. Next, the Indian Council of Agriculture Research, ICAR, and the Indian Council of Medical Research, that ICMR, Indian Council of Social Science Research, ICSSR, Indian National Academy, Science Academy, that the INSA, and the Indian Space Research Organization, ISRO. And next, there is the Ministry of Environment and Forest, MOEF, and the National Board for the Higher Mathematics, NBHM, and the Naval Research Board, NRB, and the Petroleum Conservation Research Association, PCRA, Science and Engineering Research Board, SERB, Tata Institute of Fundamental Research. These are the important research funding agencies that we should be aware if you are going to do the research on nanotechnology or any branch of science or arts. You should know these agencies so that we can get the fund from these agencies. But one thing remember, whenever you are preparing for this, you should go some study. At least 1 to 2 months go to study on that point or topic on which you are going to take the fund. And remember that if you have planned, a good planning if you have done, that is good. But there should be presentation. What is problem that during the funding, we go on to just take the print out from the computer, and then we go on to staple and then give to the funding agency. That is not showing the good way of the presentation. So you should have to send in proper way as we are handling the students, as we are accepting the proper binding and other things, taking the BTech or MTech degree. So we should have to be like that. We should have to prepare like a student, so that the funding agency also we want to seriously take. So I think that there should be a proper good paper. You use a good printout should be taken, and colorful, if possible, the colorful printout to be taken. And proper binding is made before sending your detail to the funding agency. That give a good impression. So we should do that thing. And next thing, what I say, whenever we go on to present, we should be updated, and what we are going to present, we should be prepared for that thing in a very serious way. Seriously, there we can be recognized. So they are, funding agencies are also giving, but they need some type of updated knowledge and this market also. So we should take care of that also before sending any detail of the of our research project to the funding agency. Next, this is the mechanical engineering department is organizing this program. So here I want to explain some very basic thing, that shape memory alloys that here we have already used so many times in the presentation. Even organizer is having the presentation on this topic also. So basically, it is an alloy that can be deformed when cold, but returns to its pre-heat form. Remember, shaped and heated. It is the property, basically. It is also called as the memory alloy or a smart alloy. Example you can take as the copper, aluminum, nickel, and nickel titanium, NITI, NITI. Very good example here. In second terminology, using super elasticity, pseudo elasticity. It is an elastic response to an applied stress caused by a phase transformation between the austenitic iron alloy and the martensitic, that is the hard steel phases of a crystal. This is superelasticity. Next, very good terminology is the quenching. Quenching is very simple process. It is the rapidly cooling of a hot metal. These are the three, I think, very important topic, very important terminology used in the mechanical engineering regarding the nanotechnology that I have explained here. Next is the ceramic engineering. This FDP is considering this mechanical engineering work and the ceramic engineering also. So I have given a brief introduction about the ceramic engineering, and I am having very less time to explain that thing. So here I will give only the basic terms and what practically in the research point of view the ceramic I will give that we should consider. First we take the introductory part. What is the ceramic material? Ceramic are non-metallic inorganic solids. The ionic and covalent bonds of the ceramic are responsible for many unique properties of these materials, such as its hardness, high melting point, brittle. Brittle is the property that it makes it weaker. And other things are the stronger. That is the property of the ceramic material. Other the low thermal expansion and good chemical resistance. That is corrosion free. Things can be prepared. And the low conductivity of electricity and heat. An example that is the earthenware, porcelain, and brick. They are mainly important examples that are generally used when we think that what is ceramic. Then we have in mind that some chini cup and other things we have in mind comes, that is the porcelain and other things. That is the basic ceramic. And about the classification of the ceramic in the point of view of the research, it has been classified into the three parts. There's the oxide, non-oxide, and the composite materials. The alumina, beryllia, ceria, zirconia, elements of Al2O3, beryllia, ceria, CuO2, zirconia. These are the important parts of the oxides that we should know for the research point of view. And the non-oxide, if we are considering, there is the carbide, boride, nitride, silicide. These are important non-oxides that are used in the ceramic. And here the composite material, particularly the fiber, reinforcement, combination of oxides and non-oxides, these are the composite. And applied ceramic, that the electroceramic, bioceramic, glass ceramic, refractory ceramic, nano-ceramic, these are the things that we should be aware of. That one basic thing there is used the calcination and the sintering. I was thinking that the calcination process, the temperature that already we have discussed, that is below 1000, that is okay, and the sintering, that is about 0.5 to 0.75 times that of the melting point of the chemical that we are using. It doesn't mean that if you are making a complex and you are considering the melting point of the highest melting point. No, you first find out the material which is having the lowest melting point. On that material, on the basis of that, we go on to calculate that thing. Another important thing that during the calcination, after the calcination, we should do the XRD, whether we are getting the proper composition or not. Another thing that the ball milling also occurring before that, we want to mix the basic process what is occurring that we are going to mix, and after the mixing, we go on to give them ball milling. After then, we go on to again calcination we are doing, and calcination. After calcination, the oxide form is removed and go on to proper bonding occurs. After then, there is then we go on to pelletization. That is a very important process. We give pressure and then we get the pellet form. And how much pressure is given and what is that? That is again one important thing, that is a calibration. We should try to do some calibration. If we have calculated like that, if we have calculated for the calcination, there is around 800, it's okay. So we should try to give the calcination in near about the just before 800, the 700 we should start 700, 750, 800, 850, 900, and in all these four combinations we go on to XRD and calibrate at what temperature, we are getting the best result. That is the calcination. After then, if we go on to sintering, it's okay if we have finalized that this is having the good calcination temperature. After then, pelletization, again we should have to calibrate the pelletization. If we have decided that there is some pressure that we are already going to literature search and we are getting them that how much pressure they have given, we are getting. But despite of that, we should calibrate about 4 to 5 samples. At least we get if we are getting some pressure, then we have to +2, -2. This type of sampling we should do and check the density. If we are making some pellet, there we should calculate the crude density, green density, what is coming. And that way we check at what pressure we are getting the best density. Because density is very important in the ceramic point of view. So after then, when we are getting that thing, when finalize the pelletization, after then again we go on to sintering. Again in the sintering, if we are getting, that is the formula, that is 0.5 to 0.75 multiplied by the minimum most chemical that we are using for our study. That melting point we calculate, and according to that we do that thing. And on that temperature, even that, because there is range 0.5 to 0.75, so we should again calibrate, try to calibrate that process, so that whatever we are getting, we should check the density at what temperature after sintering we are getting the best density. Higher the density, higher the strength, higher the hardness. So we should check that thing. This is the basic process we should take in consider in our research if we want some very good results. After then, there is defects in the nanocrystalline material. I want to show this thing. This is the very important part, that the zinc oxide is an extremely versatile N-type semiconductor material with a large exciton binding energy of 60 mega electron volt and a large band gap energy of 3.37 electron volt at room temperature. This is the unique property of the zinc oxide. Another thing, melting point and boiling point decreases in nanoparticles. Solar cells are very important part of this research. Solar cells work on the principle of photovoltaic effect. The conductivity of the photoconductive material increases when light strikes on it. Another very nice terminology used, we should know this terminology also, halides. Halides are three-fold coordinated network of carbon atoms generated by a periodic arrangement of pentagon, hexagon, and heptagon. Okay, another thing in the defect, there is also the same terminology as we have used there, the 0 dimension, 1 dimension, 2 dimension, and the 3 dimension. And dimensional defect, what is occurring? According to the dimension, at 0 dimension, there is a point dimension defect is occurring. At the 1 dimension, the dislocation is occurring. And at the 2 dimension, there is a surface or boundary is occurring. And 3 dimension, that the volume specifically. Another thing I want to share, that whatever the presentation I have given, and further I'm going to give the other also, that I have already shared in my YouTube channel. You can note on the YouTube channel also. ESEWFS. You can join that also, and if you are interested, you can read these slides on that also. Next is the artificial intelligence. It is also very important part of our study. So we should know about the artificial intelligence also. artificial, there's the deep learning, in the deep, in the inside part, and that is covered by the machine learning and artificial intelligence. Another terminology is used like the supervised learning and the unsupervised learning. Okay, see this, there is in the supervised learning, there is a regression and the classification. And the developed predictive models based on both inputs and output data. That is the basic thing of supervised learning. And another is the unsupervised learning, that they discover an internal representation from input data only. This is the unsupervised learning. Supervisor, we know that when we are doing the PhD, supervisor. Like that, the terminology is saying the supervised and the unsupervised. These things we should know. Another thing that is the unsupervised, there is a clustering. Thank you.
Yeah, thank
Hello, thank you, sir.
Thank you. I have completed my presentation in time, sir.
Raju sir will take the session now, and briefly I will give introduction about Dr. T.N. Raju.
just a minute, Professor Gowda.
Yeah.
Just a minute. Yeah, I take this opportunity to congratulate Dr. Pankaj Kumar, who within a short span of time has given a brief introduction about nanomaterials. He has also touched upon quantum, quantum like quantum dots, right, nano dots, and he also touched upon artificial intelligence, right? Nice to see. I think Professor is working on artificial intelligence also. Very nice topic, sir, where you have emphasized the brief thing about nanomaterials as well as artificial intelligence. If any participants have any question, you can just pose Professor Pankaj Kumar Singh, so that we'll move on to the next session. I will not take much time, and we will move on to the assessment part. Any questions by the participants? Prakash sir, you have raised your hand. Can I know what is the query? Okay, if no queries are there, thank you, Professor Pankaj Kumar sir, for your
Thanks,
wonderful speech. Shall I take, sir, take over?
Yeah, thank you, Raju sir. So now the Dr. T.N. Raju will take the session. Before that, I am going to give a small introduction about Dr. T.N. Raju. Dr. T.N. Raju is Associate Professor and Head in Department of Mechanical Engineering, Dr. Ambedkar Institute of Technology, and is having experience of 22 years, and academic qualifications include he got PhD on shape memory alloys from IIT Madras in the year of 2013, and he got ME in Manufacturing Science and Engineering from Bangalore University in the year of 1999, and he got BE in Industrial Production from Bangalore University in the year of 1996. And his areas of research includes shape memory alloys, composites, non-contact power transmission, material science, and biodiesel. And he has number of publications, which are some of them which include effect of temporary addition of iron on shape memory characteristics of copper aluminum alloys, and shape memory characteristics of copper aluminum ferrous shape memory alloys with the variation in aluminum and iron, and effects of microstructural changes on shape memory properties of copper, zinc, nickel shape memory alloys. These are some of the publications he has been made, and there are so many publications he has done, and he is having membership of professional bodies. In that, some of them are ISTE as a permanent member, ISAMPE as a permanent member, ISSS as a permanent member, MIE as a permanent member. And he also funded projects undertaken. Some of them are first one, development of proof of concept of non-contact power transmission for a typical cyclic test facility that is completed, that was sanctioned by DRDO. And another one, studies on gadolinium oxide doped zirconia thermal barrier coating, and this project is also completed. Synthesis and characterization of new biofuels for their uses in automobiles and diesel generators. This was funded by DST, and this is ongoing project is doing. And his outreach activities, which includes, he is a member and chairman of the committees, which includes academic council member Dr. AIT, BOS member SIT Tumkuru, MPCCC member Dr. AIT, faculty advisor E Shikshana VTU, doctoral committee member Reva University. And he is also given lecturers as a resource person in as a keynote speaker, invited lectures, delivered talks at various FDP programs at SJCIT Chikbalapur, SIT Tumkur, Rajarajeshwari College of Engineering, and Reva University. Session chair in third international conference and advanced materials. And he has also conducted a number of seminars and conference organized. So with this introduction, and I welcome Dr. T.N. Raju for the session, sir. I welcome you, sir.
Thank you, Professor Goda, for a brief introduction. Now I would like to start the session. My session will be a brief talk about fabrication and characterization techniques. First of all, I will not go into the high level of research, because as I see, most of them are starting young budding researchers. I would like to touch upon some of the a little bit of characterization techniques, how to go about different characterization techniques in relation with shape memory alloys, because that is my area of interest. I also work in the area of rotor dynamics and foil bearings of late. Let me start my work, my talk. Let me share my screen. I hope my slide is visible. My slide is visible. Okay, let me start. Today's topic will be on fabrication and characterization techniques of smart materials, right, basically. Now, I will directly jump into my topic, that is shape memory alloys, how I have gone about fabrication of one of the shape memory alloys. Right, I was given a task of fabricating and coming out with a shape memory alloy, which must be cost effective, that is low cost, as well as to cater to the higher temperature. Because as you see that most of the shape memory alloys, either to what we are seeing, either they are low temperature shape memory alloys, right, or they are below room temperature shape memory alloys. So my interest was to look at some of the materials that can be probable materials that can focus on especially high temperature applications. We made a simple, humble attempt, and we tried to discover especially copper-based shape memory alloys which can cater to high temperatures. Now, as you all know that either two, so many people would have talked on shape memory alloys, and they were major focusing on like NITI alloys. And I think as far as my knowledge goes, there is no substitute till now for NITI alloy. However, there have been so many attempts in the research to nurture these copper-based alloys. And basically, the copper-based shape memory alloys, you have a system what is called as copper aluminum system or copper zinc system, which are the two very popular binary systems which are available as shape memory alloys. Now, as you can see, most of the literatures, you don't find copper aluminum as a binary shape memory alloy. Always this binary is associated with a ternary. Now we have to figure out why we basically concentrate on adding a ternary element to a binary system, right? That is what we need to understand. So we need to see why you add a ternary element and why you add which element you add. Why? What is the purpose of adding that? That should be our main focus. Now, as you see that, you need to satisfy few things whenever you want to realize a shape memory alloy. Now, what happens is, so it should possess some basic characteristics which which is suitable for to show shape memory property. One is you have seen most of the people would have talked about twinning, martensite, austenite. So it should basically possess two phases. That is, one is austenite, one is martensite, and more importantly, this martensite phase, what you see, that is a lower temperature phase, should possess what do we call it as a twinning structure. Now, once you have a twinning structure, there is flexibility for movement of atoms. So it will aid in recovering your shape memory. And it should show what is called as displacive diffusion, right? Basically, right? Displacive movement, basically. Whatever the atoms they try to move, they move in a coordinated manner about interatomic distance. When you observe microscopically, they move in terms of interatomic distance, but macroscopically, what you see is a phenomenal change in the shape. This movement can only be achieved by having a twinning structure. So that is most important. And we have observed over the years, what are all the shape memory alloys, what we have seen till today, they are all based on intermetallics. They try to exhibit something like a chemical formula, right? So another important property which a shape memory alloy should have is change in interchange of crystallographic structures. That is, it should exhibit one crystal structure in its austenite phase, and it should exhibit one more structure in its martensite phase. And in order to realize a shape memory effect, your twinning structure should be thermally elastic. So we call it as thermoelastic martensite. If at all you need to have this one shape memory effect, you need to see that the kind of twin structure what you have, they should be sensitive to thermal stimulus, and they should give response to that thermal stimulus. So it should basically be thermoelastic. If it is not thermoelastic, it may not exhibit shape memory effect. Be particular, it is shape memory effect. I think Professor Pankaj Kumar Singh was referring to shape memory alloys. In his thing, he referred about iron-based shape memory alloys. See, iron, manganese, silicon, cobalt, nitrogen, they have added carbon, they have added so many manganese and systems and all to iron. But the basic, most of the time, the basic problem with iron-based shape memory alloys is it is not thermoelastic, but it shows the other property, that is super elastic. So you should know that a shape memory alloy basically exhibits two unique properties. One is shape memory effect and other is super elasticity, which is also termed as pseudo elasticity, because when you unload it, you don't see that phenomenal strain. So they use it, some people use it pseudo-elasticity, but now according to the recent research, most of the people, they try to interpret that as super elasticity. But when the earlier research started, people used to refer it as pseudo elasticity, right? Then most of these alloys, what you see, the shape marine alloys are beta based alloys, right? So these are some of the requirements what you basically see in order to have a alloy system to exhibit shape marine alloys. Another important parameter which is required, it should be highly ordered structure. Only these kind of highly ordered structures some do exhibit, not all highly ordered. Some of the binary highly ordered systems do exhibit shape memory property, right? Now, why we add a ternary system here? You are looking at the phase diagram. I mean, you're looking at the phase diagram, look at my mouse. This is the beta region. What is it as beta and in bracket A2 region? Well, so you have the composition range, right? If you go down, it is a little bit above 10 weight percentage, and here it is a little bit below 15 weight percentage. So in this region and above 600 degrees centigrade, 450 or 500 degrees centigrade, you see that beta phase is available. Once you try to start cooling, it narrows down, right? Now, that's why I'm telling this is the beta phase. So most of the shape memory alloys are all beta based alloys. When you cool, there is an ordering reaction where your beta will get converted into beta 2 phase and beta 2 to beta 1 phase. So the order reaction is beta 2 to beta 1 phase, or A2 to B2, B2 to DO3 or L21 structure, right? Now, when you cool it to the room temperature, right, you can see that upon cooling, it's depending upon the composition. Here you can see that 3 types of martensite do exist. Depending upon, you should be careful. You could look at the figure here, what I am showing on my mouse. So it is alpha 1 prime, beta 1 prime, and gamma 1 prime. So upon cooling, this system, especially copper aluminum system, by varying different weight percentage of aluminum, you can realize different types of martensites depending upon the composition, especially between higher than 10 and below 14.5 or below 15 weight percentage of aluminum. So you will see that the shape memory effect is realized only when you are operating within above 10 and below 15 aluminum weight percentage. If you go below that or if you go above that, you can't realize the shape memory effect. So this is about your phase diagram and your ordering reactions. Now if you come to its crystal structure, when you heat this copper aluminum system, binary system, so you can realize that at higher temperature it is highly disordered state. You can have either copper at the corners or aluminum at the corners. If copper is present here, aluminum will be at the center. So it is this structure, we call it as A2 structure. Now upon cooling, when it comes to B2 structure or beta 2 structure, it becomes slowly slightly ordered, and you can see that either the corners are occupied by copper and the center will be aluminum, or aluminum would have occupied the corners and the center would be copper. There is some kind of orderliness. Here you can see you are not seeing any blue color in the center. Here the corners or the center may be occupied by any atom of copper or aluminum, but here this structure, B2 structure, keeps on repeating, and you can see that repetitiveness is there throughout its crystal structure, and thereby it is going to get ordered structure. Upon further cooling, this structure tends to become a DO3 structure, which is indicated below here. The detailed DO3 structure is indicated along with the places where the atom might go and sit in its place. So the ordering reaction here will be beta to beta 2 to beta 1 phase. So essentially A2 to B2, B2 to DO3, and this DO3 structure usually will be of the phase of C3AL. Now, When you look at uh, the structure, right? Now you can see that uh, the structure, it exhibits, as I told you, alpha 1 prime, right? It exhibits beta 1 prime, it exhibits gamma 1 prime. This two-head structure is gamma prime structure, and this 3R structure is alpha prime, and 8 is the beta prime. You can see the kind of orderliness and placement of atoms. This, whatever length you see, this orderness keeps on increasing. Because this is basically intermetallic one, and if you see that this is also having a high ordered structure. Now when we read about the basic, most of the all intermetallics as well as ordered structures are very hard and brittle. Now since these are very hard and brittle, you can't make them into desired shape, right? So now I need to have a mechanism where I can make this system to my desired shape, to my desired this one wish, so that I can realize shape memory along. So if I want, first of all, if I want to process it, might be if I want to make it into form of a sheet or a rod or a wire, some deformation should happen. If it is very hard, apart from having a high hardness, it also has high brittleness. So it easily breaks. Now this is not, then I can't wound this into, if you are drawing into a wire, I can't draw it into a wire, you can't make it a rod, you can't make it a sheet or a plate or something kind of a thing, because it is not ductile. Now, how to make this ductile and also see that without compromising on shape memory effect. So the idea here is to strike a deal between shape memory effect as well as ductility should be brought in. So what we do, we try to break this order structure in the middle, so that once this order structure is broken, it loses its brittleness and try to become ductile. Now this is my this was my objective, to synthesize, to do some thermal treatments, aging treatments, to realize shape memory effect, what is the amount of shape memory recovery, whether it shows super elasticity, what is its mechanical properties. Now important thing is to study about the morphology of the type of martensite it is going to form, and what is the effect of aging, and also to little bit extent study its damping properties, because you know that shape memory alloys are basically used for damping applications. So we thought that even damping property of this alloy system should be studied, and at last we tried to probe whether this can have any use for biomedical applications. So we did little bit of corrosion studies, right? And we also tried, as in the earlier talk of today, where Dr. Venkatesh Karodi was speaking about grain refinement. To improve its mechanical properties, we also looked at refining the grain structure, because generally when you synthesize or fabricate a shape memory alloy, what especially non-ferrous alloys, what copper-based alloys, you can see that the grain sizes were very huge. So whether we can try to decrease the grain size by doing some grain refinement was our primary objective, and see what happens if you look at grain refinement, what will be its effect on the shape recovery, as well as the stresses, shape recovery stresses, as well as its force. So we try to create a simple setup to measure the stress recovery stresses and the force, so we could evaluate our system. Now, this is the methodology what we have seen. We first synthesize the system, then we try to, once we have synthesized, we try to homogenize the system. Homogenization, as you know, is a process where we need to bring some compositional homogeneity throughout the system. So once the alloy system were casted by ingot metallurgy route. So we used basically air induction furnace and argon atmosphere to see that no contamination was there, especially through air. And the next part was, once we fabricate this, we should know whether we have done, whether the obtained alloy system confers to the composition what we intended. Because see what happens during casting, there may be so many losses, and uh, what happens upon testing, we observe that there will be variation in the composition. So it becomes prime importance to see that, because since shape memory effect is heavily dependent on composition, we need to first ascertain its composition, then try to do secondary operations so that we can shape them into desired shape, right? Might be a sheet, wire, might be in terms of hot rolling, betadizing, and step quenching, and then try to, once we roll, take out a small piece out of that and try to determine its transformation temperature, especially martensitic start, martensitic finish, austenitic start, and austenitic finish through a DSC, that is differential scanning calorimetry. Then once we will see what is the transformation temperatures, we can go to the identification of the phases, whether, because only when we know that a particular phase, especially in this case CU3AL phase is formed, then only it can realize shape memory effect. So we need to identify the phase. Whatever you do, even you do any alloy, aluminum alloy systems, you take 6 series alloy or 7 series alloy, right? Or 2 series alloy. First, you need to determine its composition and see, by doing a simple XRD, you need to identify the phase. Now, once you identify that particular phase is there, you can try to do microstructural analysis using any of the techniques like optical microscopy or scanning electron microscopy or the transmission electron microscopy. Then once I see what is the nature of the martensite form, that is the morphology of the martensite form, I can do shape memory effect, I can do, test it for its super elasticity, and then try to do other processes where it gets affected, like aging. So aging has got a very profound impact on the shape memory effect. So we need to evaluate what is the effect of aging on the shape memory properties, and can we also look at the kind of thermal treatment has got any influence on shape memory effect as well as super elasticity. Then, as I was telling you, shape memory, since the shape memory alloys have got a twinning structure, where you see that there is coordinated interatomic movement of atoms. This movement of atoms helps the alloy system to absorb heat, the vibrations, and dissipate this vibration in the form of heat by movement of what you call as martensitic plates. So this study, this tells that this have a very good damping capability. So we try to explore its damping characteristics, effects, and also what might be the effect of aging on damping characteristics. And at the last, as I told you, what will be the effect of grade refinement? So we added it as a quaternary addition. Then we try to correlate our microstructure with mechanical properties, corrosion properties, recovery structure, etc. Now you can synthesize a smart material using different techniques, right? You can do it by ingot metallurgy, and you can do it by powder metallurgy. You can do mechanical alloying, you can do combustion synthesis. If you want to develop some thin films, you can do physical vapor deposition. And once you do that, in order to realize the particular shape and size, you need to do some secondary process. It may be rolling, wire drawing, or extrusion. Now, especially when you are talking about fabrication of a shape memory alloy, and especially in relationship with nickel titanium alloys. See, Copper-based alloys you can easily fabricate using simple metallurgy route, that is casting route. But you can also fabricate nickel titanium alloy. But the very uh, fact is that it's titanium, as you know, that it is highly oxidizable. So it easily picks up oxygen from the atmosphere and try to become titanium oxide, and thereby it will not form NiTi alloy, because most of, I think, earlier speakers would have referred that nickel titanium alloy should have 50% and 50% atomic Ni and Ti. Now, once a Ti becomes O2, TiO2, then you see that weight percentage or atomic percentage of your Ti comes down, nickel percentage goes up, then it may not show shape memory effect. So we need to ensure that it is free of oxygen, and thereby you can't easily melt nickel titanium using air induction furnace or any other simple techniques. You need to have a vacuum induction furnace where you need to create vacuum. See my picture in the center, what I have shown shows the vacuum induction furnace, right? So here we try to create vacuum, right, to the order of 10 to the power of -5 using rotary pumps and diffusion pumps, and that vacuum condition we try to melt nickel titanium alloy, so there is no contamination of oxygen. It may be C, N, O elements. There will be no contamination. Of course, your copper-based alloys can be produced using air induction or mechanical alloying. Even nickel titanium can be produced by mechanical alloying. You can also produce nickel titanium by you can produce also shape memory alloys by combustion synthesis, where it is fast, right? Now, as I was telling you, characterization. See, whenever you are doing any material science or metallurgical property evaluation, the first things that comes to our mind is what I'm doing, how to identify it. Now, one of the technique to identify the phases is XRD. So, the first and preliminary thing what we need to do is identify which phase it is. So, I mix copper, aluminum. Now I mix iron. As I told you, iron is mixed to bring down the orderliness and try to impart ductility. Now I should see that whether Cu3Al or Cu3Al Fe is formed or not. Now, how to identify that? Without doing any microscopy, the first thing what should I should do is to see that, do a XRD and see that the Cu3Al is formed. So phase identification is the first and the foremost thing which need to be done. As you have seen, as you are showing, this is an XRD where you have X-ray tube which produces the X-ray, and you have a sample stage here. This is a sample X-ray collector, right? So whenever you switch on the machine, it should be it is a lead coated chamber, right? So that the X-rays doesn't harm you. You should be careful while operating XRD, right? And then once you do XRD, you have to take the data from the machine and try to do some analysis of the obtained results, so that we have to do some kind of comparison. So how to do that? Now, if you go at the machine level, you need to understand some of the things here. Two types of concepts are used here. One we call it as theta theta. Theta theta means here the X-ray producer or the X-ray emitter also moves by theta degrees, right? And the absorber, that is once the X-ray falls on the sample and it gets diffracted, basically it is why we call it as XRD is diffraction happens. So what are the diffracted rays should be collected in a collector. So this is the collector, and that also moves by theta. Then we call it as theta theta system, right? You have another system where if there are two types of systems here, right? That the detector, this detector, if the emitter or the X-ray tube moves by theta, the detector moves by 2 theta. We call it as theta 2 theta system. So first and foremost thing is it should satisfy Bragg law, that is 2d sine theta is equal to n lambda. Diffraction should happen, and once it happens, there is interference of this rays, and it falls on the detector, and you see these kind of peaks below in my figure. So you find the peaks here, and these peaks will be from only particular diffracted planes. And since you find peaks from a particular, that is diffraction happens from particular plane, you see the peaks at some particular angles only. So this is one of the identification, because each element or each compound or alloy system has its unique values at which it exhibits this kind of peaks. So by matching this peaks, we try to determine from which planes the peak is coming, and we call something called as extinction rules. Now here on my figure you see it's from 111, 111, 200, 220. So this is from a FCC crystal structure. So if you tell what is the extinction of a face-centered cubic, it is 111 plane, diffraction happens 200, 220. On the other hand, if it is a BCC structure, the peaks will prop up at 110, 200, and 211 plane, right? So like that, HCP has one extinction rule. Similarly, orthorambe could have one. So it goes on. You find all those things, details in JCPDF file. That is Joint Committee for Powder Diffraction. So here is a basic information. If you take one of the system, what my system, that is CU3AL system, all the information relating to this, some people would have conducted diffraction and they would have recorded it. Only thing is, when I do, I should compare these data. What data I need to compare? The important thing is, as I told you, each element or alloy system or any compound has got distinct D values. This D refers to your interplanar spacing, and you have the intensity at diffracted planes only, and at particular planes also. So we try to see that whether these spacing matches, and this order of intensity is like first three is having the first intensity. So this is as B1, we take it. The next intensity is at 50.842, the second intensity, and then is 30 at 63 degrees, right? So then we compare these D values with the JCPDF file what we are having, whether it's D spacing, the theta, and the intensity matches, and then do some calculation and try to figure out whether the phase what we are seeing is CU3 phase or not. Then we do a differential scanning calorimetry to identify the transformation temperature. Here, in a differential scanning calorimetry, you'll be having two systems to keep the pans. Basically, if it is low temperature, that is room temperature to 600 degrees centigrade, you'll use aluminum pan. If you are going up to 1800 degrees, you will use zirconia pans. So one is kept as reference, and other is kept as the pan with the sample. Both are heated. The heat is supplied to them equally. So then one would have got one temperature. The empty pan would have attained one temperature, whereas the sample in another pan would have attained some other temperature. So this difference in temperature, we take it and try to determine the transformation temp. If at all any transformation is happening at some particular temperature, it may undergo some endothermic or exothermic reaction, which will be indicated by a peak. So in this DS, you have two types. One is called as heat compensated, and other is called as power compensated as DSC. If you are measuring the heat difference, we call it as heat compensated. If you take what is the power required to heat the sample in the pan to the temperature of a reference pan, that is the empty pan, then we call it as power compensated DSC. Now this is one particular graph where you can see that whenever you do the DSC of a typical polymer, or basically this we are seeing is kind of a polymer where you observe a transition temperature, that is glass transition temperature. Glass transition means it's softening of the material, and you can see further heating, it will see crystallization is there, and further you heat, it will undergo melting. If you do the reverse one, then again it crystallizes. Then once it crystallizes, again it softens, and then it becomes solid. So there is solid to viscous, viscous to crystal, crystal to melting, and liquid. Again back, the same thing happens. So you can do both heating and cooling cycles and observe that what are the transitions are happening, or the transformation happening in the system. Then we can, of course, do scanning electron microscopy, take a secondary image using scanning electron microscopy, or if you can observe the backscattered electrons, we can do EBST and take a atomic contrast micrograph to have a comparison. So it will give you both atomic contrast as well as the morphology of a material, and it has got other special properties. It has got EDS. EDS, people usually tell EDAX, it's basically EDS, that is energy dispersive spectrometry, through which we can identify which elements are present. We can't determine the composition because depending upon the focus, the peaks may be more or peak might be less, whether it is a spot you are seeing or area you are scanning, it all depends. So you get a first-hand information about the nature, what are the elements present in that system, apart from seeing the morphology. This is one of the sample stage where you can mount your SEM samples, and another characterization technique which we basically use is transmission electron microscopy, because you can see that whatever which can't be revealed by scanning electron microscopy beyond 1 lakh magnification, and if you want to look at atomic level, or you want to look at stacking parts, right? You want to look at dislocations, which is not possible by scanning electron microscopy. We can look at transmission electron microscopy, right? And this is the sample holder. What sample you are going to prepare, you can see is this. Here you can see the sample holder. It will be some 3 mm diameter, where you can, if you are doing a metallic sheet sample. So we need to cut and polish it to less than 100 microns using a twin jet polisher. You need to create a hole, and what you are looking at the area is at nanometric level. Very small area you look at, you can see here the holes, it will keep the material here. Now this is one kind of observation where you are seeing the stacking faults. You can see I have shown through arrow mark. This is one nature of stacking, and this is another nature of stacking. So you can clearly observe the stacking faults here. Here also you can see how stacking faults are clearly seen. And another thing is you can see these dark, small lines, right? And here in the last figure also you can see these kind of lines. These small thin lines, what we are seeing are dislocations. And again in my second figure below here, you can see again the stacking faults here. Here you can see again the stacking faults found here. So you have to carefully observe. Here again you can see a thin line here. This is a scratch, not a dislocation. This is right what you are seeing here, where my mouse is moving, is a scratch, not a dislocation. Some people see, most of the time these micrographs are qualitative analysis. If you interpret wrongly, then it is a bad interpretation. So you need to be careful while interpreting micrographs. Now here you can see I have taken a precipitate and dislocation in a precipitate. So beautiful micrograph where you see how it's like a stitching of a precipitate. These are basically black lines are dislocation. See how nicely they are moving towards the edge of the precipitate. You have seen, you can see dislocation guide, you can see dislocation forest, cut through the precipitate. So many things you can observe through the TEM, right? And you can also take a diffraction pattern to see that whether that corresponds the phase for phase identification. Right? This is some of the diffraction patterns what you are seeing. Then we can we also try to see sometimes, especially in case of polymers as well as in shape memory alloys, we try to do dynamic mechanical analysis, where you can see, you can do a simple tension compression, you can make shear, or you can do a cantilever, or you can do a 3-point bending test. Here basically what you're doing is you're applying load, right, varying load, and you can also control strain. You can apply some vibration, that is frequency, right, or you can also apply some strain rate, and you can also heat it. Thereby you can see that you can observe certain phase changes which will be indicated by a peak. And when you see such a kind of stimulus and response, the two graphs, at the bottom you can see there are two graphs, one is thick black and one is blue. So one is the response, one is the excitation. And this delta will be the indicator of your damping capacity of the material. Usually we refer it as tan delta. Two things comes here. One is storage modulus, another is loss modulus. Storage modulus, you can simply define storage modulus, the ability of a material to store the energy. Means if it is a good damping material, thus vibrations in a shape memory alloy, the plates, that is a martensitic plates, move coordinately and absorb. You require some energy, and that energy is taken from the vibration. So once it moves and there is no vibration, that has to be out. That vibration is given in the form of heat. We call it as loss modulus. So you can look at the storage modulus and loss modulus. Here is a graph where you are seeing storage modulus as well as loss modulus, and also damping capacity, which is indicated by tan delta. That is a phase difference. So I think we are nearing to our session, since we need to conduct online assessment also. At this point, I will stop my talk. Right? If you have any questions, you can ask me. I'll answer to your queries. Otherwise, we'll go ahead with our online assessment. Any questions?
Excuse me, sir.
Yeah, tell me, Amar.
So, actually, my question was based on that damping characteristic, the effect of aging.
Yeah.
Would you kindly explain that part, sir, once?
To my system?
Yes, sir.
Okay, fine. Just a second, I lost my connection. Just a second. So this Amar, if you can see, this for my chemical composition. I did two things. One is I tried to vary, because aluminum has got a greater influence here. So I tried to vary between 10 and 12.6. So what is its effects on transformation temperatures I studied? And then I varied iron content and see what is its effects on transformation. These are the two things in this work what we have seen. These are the micrographs what you are looking at. You can see so beautiful martensitic plates. You can see my cursor, and you can see three different types of martensitic plates here. See, these are thin plates, very thin airline-like structures. These corresponds to a beta prime. If it is still thinner, like a binary structure, it refers to alpha prime. If you are having a thick plate like this, like a spear shape or a band, right? So see, you can see how a spear shape is here, like a thick bands you can see, which are including one inside the other. Here you can see very clearly within a grain how thick the bands are there. So this is an optical micrograph. you can see the plates. These are gamma prime, this one, martensite. So accordingly, you can see the transformation in this DSC curve, which are represented below. If you happen to find both beta and gamma, you can see two peaks are cropping up here. Here also you can see both. You can see beta prime as well as gamma prime plates. So you see two peaks here. Right now, the phase identification has been done here. Now I will come to your question. That is, these are some TM micrographs what we did. Coming to aging, see, when we come to aging has got a profound effect, especially in terms of shape memory alloys. Because some materials, especially if you take copper, if you try to age it at 100 or 200 degree, 250 or 300, 400 degrees, some deleterious precipitates are going to form, especially which are based on Cu9 Al4. And when you keep it for a long duration of time, there is sufficient time for diffusion to happen. And the very fact that these precipitates will form and try to hinder the movement of the martensitic plates. See, I told twinning. So this twinning will get affected due to the presence of these precipitates. Once this movement of plates gets affected, what happens? The vibration absorbing capacity of the material comes down, and your damping capacity will come down. Here you can see the damping capacity. My earlier one was almost like 0.11, 0.13. Here it has come down to 0.05. The very fact that you can see these micrographs, especially the D1, you can see a lot of precipitation of Cu9Al4 are formed. So these precipitates try to hinder the movement of the martensitic plates. Thereby, the vibration absorption capacity decreases, and in order to give away the heat or the energy is absorbed, it should be given out in the form of heat. So it can't give out because it is not moving. So aging has got a profound influence on the shape memory effect, because once it can't move, it can also not show shape memory effect. It can also not show damping capacity. So its shape memory effect as well as the damping capacity drastically comes down. Here I have done at 3 different temperatures for your information. One is at 300 degree, one is at 400, one is at 500 degrees centigrade. You can see that as your white percentage, that is depending on the variation in the aluminum as well as iron, you can see profound influence of aging on the damping capacity. It is decreasing. At 300 it is somewhat okay. You can see 0.1 and 0.212 is there, whereas when it comes to 400 it has drastically decreased, and at 500 some might not at all have damping capacity. See, in this S2 case it is nil. It is 0.008 in case of and 0.009 in case of other two. So it comes down. Have I answered your question, Amar?
Yes, sir.
Yeah. Any more question?
So, but in the strain recovery at 500 degrees Celsius, all those the results are also null, sir.
Yeah, because I told you that will not give any movement of the twinning plate. Twinning will not happen. So when twinning doesn't happen, you don't get shape recovery. It's just as good as any other alloy system. Okay, you don't get, that's what I was telling you, no shape recovery, no damping capacity.
Okay.
All this happens only due to the movement of the martensitic plates. When the plates can't move, there is no exhibiting of shape memory effect as well as damping capacity. Am I clear?
Yes.
Yeah. Any more questions?
So before at the starting of your slide, there was a point like why iron as a ternary
Yeah.
alloy like this
Yeah.
element.
Yeah.
So
See, some of the materials, like if you have gone to my later slides, you would have realized I have added chromium, I have added cobalt as quaternary element. Some of these elements, when they form kind of a precipitates, might be at the grain boundary or in between the plates. and try to hinder the movement of the plates, and they try to create a strain field around the plates. Once they create these kind of strain fields, they produce a obstacle nature of the plates, then you don't realize either shape memory effect or super elasticity or even damping capacity. So we should be very careful while selecting a ternary system. The ternary system should not hinder, affect shape memory effect or super elasticity or damping capacity. And the other point is, it should at the same time should also bring in ductility into the system without affecting these properties. So both things should be, all the 4 or 5 things should be satisfied. It should also allow for displacive transformation. It should also allow for a crystallographic change. It should not hinder these properties. If it hinders, then it will not be useful as a ternary element. Especially, you can look at chromium, it hinders a lot, right? Or zirconium sometimes at higher weight percentage, it will affect. So
Yes.
we should be careful while selecting the ternary system also.
So haven't you performed any sort of electrical conductivity like sort of measurement like this?
We have done DSC, we have done strain recovery, we have done stress recovery. Electrical conductivity we could not do, right? Probably now I will try to do that.
Yes. So actually, I'm interested in this field. So can I get your mails?
Yeah, you can see in my brochure, my mail is present. You can contact
Okay.
me directly. Huh?
Okay, sure. Thank you.
Okay, thank you, Amar. I think if no questions are there, we will end this session here. And you please be careful that you need to answer your feedback both in our WhatsApp as well as chat, and even in the ATL login ID also. You should log in into ATL, give your feedback there also, and here also, and also try to attend the assessment which will be shared to you shortly. So all these 3 or 4 things should be done. Don't forget to log into your ATL and give your feedback. That is compulsory, otherwise you don't get certificate. And another important thing is, once you submit, you may not get certificate. It may take some 2 or 3 days or sometimes 10 days of time. Be patient. If you have qualified, if you have got more than 60% of marks and you have got more than 70 or 80% of attendance, then surely you will get your certificates. So we will try to wind this session with a valedictory, a simple valedictory by me itself. I thank all the participants for their patient hearing all through these 5 days and asking very good questions throughout. And I hope that I was able to fulfill your wishes or what your expectations regarding composite materials and nanomaterials, and try to expect the same from you in near future for conducting future FDP programs. Thank you one and all for your active and deliberation in this faculty development program. And in another few seconds, a few minutes, you will get the assessment questions. ATL, now after finishing, once you close that, you can directly go log into your ATL and give your feedback. That's all, no? Only feedback or ATL only? Yeah. Thank you very much for patience hearing.
Thank you, sir.
Thank you all for participating in this FDP.
Thank you so much.
Please, thank you, and we'll be sharing in your chat box the link for feedback as well as the Google forum for your online assessment. Now,
Sir, what is the time for online assessment, sir?
how much you want?
Time duration?
Basically, we have made it simple. 25 questions. Am I audible?
Yes, sir.
25 questions. Shall we take half an hour?
What will be the duration of the exam?
Half an hour. Half an hour is okay.
Yes, sir. Half an hour is okay, sir.
No, sir.
Or you want 1 hour? Okay, we'll keep it till 5 o'clock.
Okay, sir. Okay, sir.
Keep
Sufficient
it
time
till 5
Sir,
o'clock.
1 hour
actually.
better,
5
sir.
o'clock
1 hour
will be
better.
sufficient actually.
Okay, sir. Pankaj sir, tell sir.
Sir, you can give 1 hour, sir. It will be okay.
Okay, sir. Okay, one
Five
to 1.5 hours
hours.
we'll try to
It
keep
will
it.
be okay
So
for
at
me
least by
up to
5
the
o'clock,
time.
you try to finish the test, sir. Thank you, one and all. Thank you, Pankaj sir.
Thank you, sir.
My talk was okay for you, sir. It satisfied you?
It was excellent, sir.
Okay, thank you very much, sir. Thank you very much. We'll meet sometime, sir.
Sure, sir. Sure.
Okay. Yeah, Prakash, you raise your hand. Tell me, Prakash MS, you have raised your hand. Do you have any specific queries? Okay, shall I leave a meeting with your kind consent? Thank you, Kartishan, for your useful feedback. Thank you, Deepak. I hope we have started our sessions in time. 1 or 2 days might be because of the speaker's uh, problem. There was a little bit delay, but which we have fulfilled and taken extra session. I think I ask your pardon for this delay in another 2 days where we missed a few minutes of the talk. Thank you.
Thank you. Thank you, sir. Thank you very much, sir.
So, on behalf of the entire coordinating team and organizing committee, Department of Mechanical Engineering, Dr. AT, we are paying gratitude towards all the speakers across the globe who have spared their valuable time and shared their expertise with the participants. We would like to thank AICT Atal Academy for accepting our proposal and sponsoring for conducting this FDP. We would like to take this opportunity to thank all the participants who have taken time out of their busy schedule to register and participate in this 5-day AICT sponsored Atal Academy program. On this occasion, we would like to thank our management for their constant support in successfully completing this 5 days FDP program. We would like to thank our beloved principal, vice principal, and all the deans for their continuous support. Thank you, everyone. So the test link will be shared here in the chat box as well as it will be shared in the WhatsApp group. The time limit what we have, as sir told us, it will be 1 hour, after which it will be deactivated. And the final feedback has to be given in the Atal portal itself. Once the attendance and test marks is evaluated, the certificates will be uploaded in Atal portal by the next 1 week. Thank you. The certificate has to be downloaded from Atal Academy website. Yeah.
Where is the link for the test?
Yeah, we'll be sharing it now, sir.
Yeah, in the WhatsApp or in the chat box?
Both here also in the chat box as well as in the WhatsApp group also we'll be sharing
Okay.
in just a few seconds.
And what about the materials, sir? The slides, can we have that afterwards? I mean, just for reference, for enriching our knowledge, can we have that? Hello? Hello? Sir?
सर पेपर का लिंक शेयर कर दीजिए हम लोगों को सर प्लीज. Raju sir, are you hearing my voice actually, sir? I'm not getting the actually paper link actually.
तो ये वेबसाइट है, ठीक है, जो भी करेंगे और प्रपोजल आखिरी मोस्ट ऑफ नियम से यूज करना
ಏನ ರಾಮನ್ That's fine.
Thank you, sir. I have submitted my question paper as well as feedback. Please.